Now we're moving on. I think I told you before that we are going to do a little bit of differential equations right now. This is not a class on differential equations. This is a basic introduction. Some people ask me, what are the applications to differential equations? Why in the world would we even use them? I'm going to show you some of that right now. What you need to know is that differential equations do have very far-reaching applications. If you ever go into any sort of engineering, so any branch of that, you're going to be doing differential equations for the rest of your life. Yay for you. Of course, there are entire classes on differential equations, several classes on it. We are going to talk about one specific type of differential equations, the easiest, the most basic, thank goodness for us, separable differential equations. Separable differential equations. So here's what, I'm not going to write all of this stuff down, but these are kind of important little topics here. Side notes, I suppose is a better way to say it. Firstly, a differential equation is a derivative with some unknown factor in it, something that we don't know. The order, when we say differential equation of the order is the highest derivative that occurs. So if we have a first order differential equation, then we only have a first derivative in that differential equation. Does that make sense? If we had a second order, that would be a second derivative in there. Did you guys get the idea? Mm-hmm. So when we say order, I will write this down. So the order of a differential equation is the highest derivative that occurs in the equation. Let's look right now at some first order differential equations. Tell me again what first order is going to mean for us. Just going to have the first derivative up there. So first derivative and then the function itself. So here's a simple way to look at it. Here's a simple way to look at it. That right there is an example of a very, very basic first order differential equation. Do you see what, if there's is there a derivative up there? I see a derivative. Do you see a derivative? What's dy dx stand for? What type of derivative? The first, hey, look at this, first derivative. It's an equation. It's equal to some function of x. Are you guys with me? We've basically been doing differential equations this whole time. They say, hey, here's a function equal, here's a derivative equal to a function. Can I get back the function of y? Well, absolutely. If I wanted to find what y was equal to, I would just have to integrate f of x dx. Does that make sense to you? Well, that's what we've been doing integrals this whole time, antiderivatives. We've been solving some very basic first order differential equations. So a differential equation of first order says you got some equation. This is an equation. It has at most a first derivative in it. Actually, it has exactly a first derivative in it. Solve that first derivative. Solve it for whatever the function is. This is the idea here. Show of hands feel okay on the basic idea. Now this is very simple. Of course, you can really get more advanced in this. Now, the problem is here, if you don't already notice this, this only works for functions that are completely in terms of x, doesn't it? So this was pretty easy when we had integral of something with x. But if I had integral with something of x and y, well, that would be a problem, wouldn't it? Well, what in the world would I do then? Well, we're going to discuss that right now on these differential equations. So this is a problem because this would only work for functions in terms of x only. So good only for functions of x. which is exactly what that is. What if we had functions in terms of both x and y? Well, consider this. If we did that, what we would be doing is we'd have a derivative, and we'd have a function with both x and y in it. So we still have a first derivative. Hey, look at that. Is it still a first order differential equation? Let's walk through it. Is it an equation? Does it have a derivative?
Yes.
What type of derivative?
First derivative.
So this would be a differential equation of the first order. Does that make sense to you? That's all this means, guys. It's an equation, has a first derivative in it. Now, the problem here is that, well, we're going to have some function with both x's and y's in there. That's going to be an issue we're going to have to deal with, and that's why these separable differential equations are going to be quite easy for us. I'll show you them in a minute. I'm hoping that I don't intimidate you too much with the vernacular before we actually get to examples. You're going to find out that what we're going to do here is not super hard. It's going to take advantage of all the stuff we've learned, all right? So don't let it intimidate you right now. Just kind of stick with the theory behind it, what's going on. We will get there eventually. Well, then a solution would be this. A solution would be, well, it would be some function y of x. So we treat y as a function of x. You remember implicit differentiation? You guys remember that? How sometimes we don't know what y is explicitly, but we still know it's a function of x? That's kind of the idea here, is that we're going to be solving for y as a function of x, even if it's not explicitly defined. So a solution here would be something that when I take a derivative of it, it gives me back the function that I want. Here, y equals y of x is our solution. So base it on, I should wrote this, on some interval. So in other words, y equals y of x means it's a solution because when I take a derivative of y of x, it gives me the specific function I'm looking for, f of x of y. Oh, sorry, x and y. That's the idea here. Now, would you like to see an example real quick? Okay. I think that's probably a good idea to clear all this stuff up. Right now, I'm not going to show you how to do your differential equations. I'm going to show you how to check whether one's a solution or not. So, show that y equals x plus 1 plus c e to the x is a solution to y prime equals y minus x. On negative infinity to infinity. Well, golly gee, how in the world are we going to do that? Well, first things first. Do you understand that y prime is the derivative with respect to x of y? Did you guys get that? Okay. Or y prime is the derivative with respect to x of y of x, because they're basically the same thing. That's what we have over here. Y equals y of x. Well, here's what we're going to do then. What we're going to do is we're going to take a derivative of this thing. This would give us a y prime. What we're going to see is if when we take a derivative of this thing, it matches up to this thing. That's basically all it is. It's saying take a derivative, see if it matches right here. You guys with me on this one? So let's start off with y equals x plus 1 plus c e to the x. Can you tell me what y prime is? Do you guys know how to take some derivatives? Of course you do. So what's the derivative of x? What's the derivative of 1?
0.
Perfect. can you do the derivative of c times e to the x? Do you need a product rule for that?
Is C a constant? Or
C is a constant.
So no.
No. So plus what?
E to the x.
So what now?
E to the x.
C e to the x. That's perfect. That's exactly right. You guys okay with this so far? You sure? So right now we have two things. We have y prime equals 1 plus c e to the x. That's coming from this guy. And we have y prime equals y minus x. We have y minus x. Well, let's see about this. What we know, can I kind of take a little bit of these two things and move them together for you? Check this out. What we know is that y prime, I'm going to start this way. I'm going to say y equals x plus 1 plus c e to the x. True? Okay. If I subtract x from both sides, oops. If I subtract x from both sides, here I get y minus x. What do I get here?
1 plus c e to the x.
Those would be gone, wouldn't they? Do you see it? Do you see it that it works right now? It says, well, look at this. This right here, this was our y prime. That's what we started with. This right here, this is our other y prime. So basically what it says is, I'm going to have arrows everywhere, and I'm sorry about that. I hate all the arrows, but that's where it's coming from. Here's the idea. The idea says, well, check it out. If I take the derivative of this thing with respect to x, what I ended up getting was this. Agreed? If I look back at my function, and I subtract x from it, look back at my function and subtract x from it, that gives me this y minus x. Oh, look at that. My y minus x is equal to my y prime. That was our initial expression up here. Well, but also, if I subtract x from this side, I get 1 plus c e to the x, which is my y prime from when I took my derivative. Basically, it says the derivative that you get when you, the derivative you get when you take this derivative is equal to what we're looking for. It basically says that this is a solution. Therefore, y equals x plus 1 plus c e to the x is a solution to this. Now, a little bit more about the vernacular here. You guys have any questions? You probably don't even know if you have questions on this one. I want to make sure that you actually get the idea. The idea here was simply proving that when I take a derivative of this, it satisfies this condition. This is the idea. Do you guys understand the basic idea behind it? Are you sure? It's probably brand new for you. You haven't seen it, so I would expect if you have questions, now would be a good time. Anything at all? Have I explained it well enough for you to understand it?
And it wouldn't matter what C would be?
No, and we're going to talk about that right now, actually. That's a good segue. Thanks for the segue. If anyone ever wants to buy me an actual Segway, that would be cool too. I don't know why I did this, because it doesn't do that. It goes,
You just, yeah.
you should lean.
Do we get extra credit?
Yeah. Yeah, I get it.
There's like a new leaner kind of Segway kind of.
Leaner.
It's like, it's.
We like leaner.
No, like it's like.
It's called
more-
walking.
I don't know.
That is classic.
It's not as big and bulky, I guess.
A leaner Segway. I like that joke. That was funny. Whoever said that. Okay, so where are we at? Here's the deal. A first order differential equation will have a solution with one arbitrary constant. This right here is an arbitrary constant. Notice how I could plug in anything to this thing and it would still satisfy that. Still going to work. That's the idea. So, this will have a solution with one arbitrary constant. C. Hence, this is called a general, and this is called a general equation. Sorry, general solution. So for us, we'd say that y equals x plus 1 plus c e to the x is a, look at this, look at this with me for a second. How many constants do you have? One constant. Well, sorry, one arbitrary constant. And this is a constant, I know that I misspoke a little bit, but this is a fixed constant. This one does not change. How many arbitrary constants do you have? Remember that plus c you put at the end of every integral? That's an arbitrary constant. Doesn't matter what it is, you get the same thing, right? This is an arbitrary constant. There's one of them. So this right here is a general solution to this differential equation. Now you might be asking the question, at least I did the first time, well, wait a minute. If there's a general solution, can you ever have a specific solution? What do you think? If the c was a number. So if to make the c a number, we have to have what's called an initial condition. Now, if you've taken a Calculus 1 class before, which I know you all have, you've seen basic differential equations with initial conditions. The basic differential equations I gave you were these ones in Calculus 1. Where you just did an integral basically, and then you plugged in your initial condition. You're like, wow, this is really easy. Yeah, it's designed to be easy at that level. So basically, here's the idea. We have this idea of a general solution, which has your arbitrary constant in there. If we want a specific condition, so a particular solution, we need what's called an initial value, or an initial condition. By the way, the general solution gives you a family of these integral curves. It's a family of curves. Just like when you add c to the end of an integral, you get a family of curves that satisfy that condition. This is the idea here. So, for a particular solution, we must have an initial value. Initial values look like this. This is from your Calculus 1 days. It hasn't changed. Initial values look like this. They say y, when you plug in some x, some specific x, that's the x naught or x sub 0, gives you some y sub 0 value. They're actually specified numbers. So it says, hey, y of 0 equals 7, or y of negative 4 equals whatever. It's going to be something specific that you can actually plug in. So would you like to see how that actually works? Okay, let me show you that. So this gives you, basically this is what this does. This makes your differential equation pass through a given point. I'll say this again. What you're getting here, I think I went through it a little quickly anyway the first time. What you're getting here for your general solution is a family of curves. A family of these integral curves. Basically, you can plug in anything to C, can't you? Can't you? And it'll give you a different curve. At least that's how it seems to me. If I plug in 1 or I plug in 7, it's going to give you something slightly different, doesn't it? So general solution gives you a family of curves. If we want one specific curve, listen carefully here please. If we want one specific curve, then we have to make it pass through a point, one point. This is the point. Do you get the point? So what this does is this makes the differential equation pass through x sub 0, y sub 0. It makes it pass through a point. Listen to this. If I take a family of curves, this is a family of curves right here. If I take a family of curves and say, hey, here's all your infinite number of family of curves, okay? And I say, now I want you to pass through one point. It has to be one specific curve after that. You have all these curves that go like this. All these, well, it's going to hit this point only once. You're not going to cross over, otherwise it wouldn't be in the same family of curves. So to satisfy this initial value, you're limiting this to one specific solution, one specific curve. Show of hands if you understand the idea here. Now let's take what we just did, what this whole thing did, and apply this initial value to it. I'm going to try to show you exactly how this works. So first thing, in order to solve these differential equations with initial values, let's look at this just from what we know, okay? This thing right here is called a what?
First order derivative.
Okay, look at it. What is it?
Derivative.
First order. First order.
Derivative.
Differential
Or different.
equation. This is a first order differential equation. Are you guys okay with that one? What's this?
Initial value.
Exactly right, that's an initial value. So we have a first order differential equation and we have an initial value. If you're going to solve a first order differential equation, you got to have a solution to it, a general solution. You have to have something to plug numbers in. We don't just start plugging numbers in now. That doesn't make any sense, okay? What we do is we have our general solution. Now, for this differential equation, we knew that y equals x plus 1 plus c e to the x is the general solution. So we had our first order differential equation. We already knew a solution. It was kind of nice, right? We just checked it. You guys with me on this one? We just checked it. We know it's a general solution. Well, now we're given an initial value. Here's where you use your initial value. As soon as you have your general solution to your differential equation, and you have your initial value, can you plug these numbers into this?
Yes.
Yes, you can. So y equals x plus 1 plus c e to the x. Well, you better tell me what the x is here for my initial value. So y of 0 equals 0. What's the x there? 0. There's only one number, right? So either way you go, you're not going to get it wrong. But which 0 is the x? Is it 0 inside or outside?
Inside.
This is the x, this is the y. So what's x become?
0.
What's y become?
0.
Notice how if you have a function of x's and y's and you plug in everything that has an x and a y, your constant will be the only thing that you have left to solve for. Does that make sense? That's nice. That's why initial values tell you what your constant is, what your arbitrary constant is. So what's this become?
0
Plus 0. Sorry,
equals
that was wrong. 0 equals 0 plus 1. The 1's not going to change. Plus what?
c e to the 0.
Sure. So, differential equation, no problem. Got to have a general solution. Got to have something to plug numbers into. If I'm giving you numbers here, you got to have something to plug them into. Your initial value says, hey, take these values for x and y respectively, use them in your general solution to solve for c. To solve for that arbitrary constant. Let's see if we can do it. Y was 0, x was 0, x was 0. Simplify it. 0 equals 1 plus
C times 1.
c times 1. Very good. This is 1, so we're going to have c. How much is c equal to?
-1.
Can you take this and now rewrite your general solution, except without c? And instead of c, put your number in there. Yeah, that's exactly what I'm asking you for. So look what this does, okay? I'll try to explain this to you one more time. A general solution is a family of curves because you can plug any number into that. Okay, so it's going to give you a different curve for every single number you plug in. If I want to go through a specific point, it's saying now you're limiting that family of curves to one specific family. And to solve that for that specific family, you need to tell me what the C is. You go, hey, that C is the only thing that's giving you different curves, ain't it? The X isn't, the 1's not, and the E to the X isn't, the C is. So if I can find out what my C is, I can say that, well, now the specific solution, not the general solution, but the specific solution is going to be exactly what the general solution is, but going through one distinct point, 0, 0. And if we do that, we go from the general to the specific, saying, yeah, I know family, but no. I want you to go through one point. That gives me one specific curve. Show of hands if you understood what we were talking about today. Cool. Next time, what we're going to talk about, I'm going to give you a lot more examples on what we're going to be doing with these differential equations. We'll talk about how in the world to solve separable differential equations. Right now, let's not get ahead of ourselves. We really haven't done much. Okay, I've defined what differential equations are. We've shown that that we had a solution, but it was given to you. We actually didn't find that solution, did we? No, we've shown. And then we talked about what an initial value was. How if I have a family of curves, cool, I have that general solution. But if I want a specific curve, I've got to go through a solid point, fixed point. That's what the y sub 0 equals 0, or y of x sub 1 equals y sub x of 0 equals y sub 0 is. A specific point that limits the number of curves we have to 1. What we're going to do next time, again, is talk about separable, actually how to find this thing so that this stuff is possible. You guys okay with that? All right, so today we're going to discover what a separable differential equation actually is, what they look like, and how to solve these separable differential equations. So, firstly, what in the world is a separable differential equation? Well, really, it's a differential equation. Remember, we're talking about first order, so with a first derivative. It's a differential equation that can be written as a product of two functions. So when we say separable, it means that we can basically separate the variables into a product. So something times something else. So this happens when the differential equation can be written as a product of two functions. More specifically, those two functions should be one in terms of one variable and the other in terms of the other variable. So one would be in terms of, say, x, and one would be in terms of, say, y. So when we talk about a differential equation, yeah, we're talking about an equation with a derivative in there. When we're talking about first order differential equations, that derivative has to be the first derivative. When we're talking about separable differential equations, we're talking about one of those first order differential equations for us, where we can write that differential equation as a product of two functions, one in terms of x, the other in terms of y. That's basically about it. Let me give you specifically what we're talking about. If we have a separable differential equation, one of these two cases will be true. Either we can write it as dy dx, our first derivative, is a function of x times a function of y. Here's what we mean by separable. Separable means that, do you guys see what we're talking about? These two functions, the one's in terms of x, one's in terms of y. Here we have a function of x times a function of y. It's a product. Or if you do a little bit of math magic with this, you can also get a different format. Or, basically, if we divide here, multiply by dx over here, and then subtract one from the other, add one from the other, we could get this. A function of x plus a function of y. You can show that these two things are equivalent. So, I know I said a product of another, but you need to know that you can take this and write it this way. So we could take this by doing a little bit of math with it. You can change this format into this format or vice versa. Show of hands feel okay with these two formats. So this is what separable means. Basically it says, okay, we have a function of x times a function of y, or we have a function of x dx plus a function of y dy. Just caught it. I like x's. Can't blame me. dy. Right now, we're not going to work with these things, but I want to give you examples about what is separable, what is non-separable. Okay, so here's some separable differential equations. So if we take a look at these two examples, if I were to give you x squared plus 1 dx plus 1 over y dy equals 0. That right there would count as a separable differential equation. You see that it fits one of these formats. It's not the product one, because we don't have a dy dx equals something being multiplied together, but it is this one. It's a function of x. Are there any y's over here, or any dy's over here? That's what we're looking for. Are there any x's over here, or any dx's over here? That's what we're looking for, so that we can separate them into two different groups, either by a product or a sum or difference. You guys okay with that one? This counts as a separable differential equation. Or something like this. Even something so basic as dy dx, and we're going to work with this one later, equals k times y. That right there is something that's directly proportional. We're going to talk about proportionality in just a little bit, one application of this. Well, if you think about that, we have, what is this? ky. It's a product. Yeah, it's a product. So we could define k as being a function. Oh, you know what? Let me change this. Let me change this to a t, because we're going to be relating this to time. We could change this to k is a function of time, where k could change with respect to time, and y would be some function in terms of y. So we could have two different functions out of this thing, k being a function of time, y being a different function with respect to another variable. We're going to deal with this in just a little while. But what I want you to notice is that these two things are actually separable differential equations. All x's, all y's. A function of t, a function of y. This is the idea. Show of hands if you feel okay with the idea. It's probably going to clear it up if I give you some non-separable as well. So these are separable. Differential equations. Of course, we have some ones that are non-separable. So, for instance, if I had dy dx equals that one, something like that, where I have xy squared. Right here, look at it. Look. Separable or non-separable? Separable, for sure, because it's x times y squared, no problem. I can isolate my x's and my y's by doing just a little bit of division. So basically I could divide over y squared, I could multiply dx over here, and I'd have y's on one side, and I'd have x's on the other side. That's the idea. That's what separable means. We can get y's on one side, x's on the other side. Quick head nod if you're okay with that one. So that's what you can do here. If I just divided by y multiplied by dx, or if I just added or subtracted one of these two things, I'd have them on completely different or separate sides of my equation. That's our separable differential equations. So far, so good? This one you can't do that with if I add a 2. If I add 2, well, that's a problem. I can't get these two things to work nicely with each other. Or if I do something like this. Also not okay. We have x's and y's together. We can't separate those things. Show of hands feel okay with this one. You know what? Yeah. There, that's even more clear, just so you know. The first one I wasn't sure. I don't know, maybe I made a typo on that. Definitely non-separable. So we have separable, no problem. We have non-separable. Now, what I'd like to do is do a couple examples of how to solve these things, just so we get our feet wet with it. So we're going to talk about right now how to solve our separable differential equations. So let's suppose we start with something that looks like that. How in the world are we going to do this? Well, the idea is what we want is we want to have all of our x's and dx's on one side and all of our y's and dy's on the other side. So basically, if I have dy dx equals g of x times h of y, well, this right here, this means it's separable because I can get all my y's on one side, all my x's on the other side, hence we can separate those variables. So this is how to solve differential equations by separation of variables. How would I move these things around? What would I need to do to get all my x's on the right-hand side and all my y's on the left-hand side? What would I do? Let's just divide by what?
Take your pick.
Take my pick. I want my x's on my right-hand side.
Divide by one.
Sure, so if I divide this, I would get 1 over h of y dy dx equals g of x. We okay with that one? Now, here's what's very interesting about this. As soon as we have this, our y's on one side or x on the other side, we can actually do whatever we want to an equation. Do you believe that you can do whatever you want to an equation as long as you do it to both sides? What we're going to do is we're going to integrate right now on both sides of our equation with respect to x. So we're going to have an integral 1 over h of y dy dx with respect to x equals the integral g of x dx. So maybe I can write a different color so you can see what I'm doing here. This same thing, yeah? We're going to integrate with respect to x. We're going to integrate with respect to x. Okay, see that I did the same thing on both sides. What's interesting about doing this, our dx's, they're gone. What that does, that changes this into an integral of 1 over h of y with respect to y. Integral g of x with respect to x. You guys okay with that so far? Now suppose that this is an integrable function. If this is true, what we're going to get here is we're going to get some function, we're going to call it capital H, because I don't know what it's going to be, but it's going to be a different function because it's integrating. Remember doing that with antiderivatives, usually capital letters from a long time back? Well, if this is integrable, then our integration is going to be h, but it's going to be a function in terms of y. Do you agree with that? Well, this is going to be some function with respect to x plus some arbitrary constant. That's basically how we're going to solve these things. We're going to get all of our y's on one side, we're going to get all of our x's on the other side, and then we're simply going to integrate. This is the whole idea. Do you guys understand the idea here? Let me do like a 20-second recap to make sure that we got this. So, the brand of differential equations we're working with are called separable. They're called separable because they fit into one of these two categories, saying I can group all my x's and all my y's on one side or the other. They're not combined together when we can't do that, where we can't separate our x's on one side and y's on the other. You guys okay with that so far? Yes, no?
Yes.
Okay, so when we have this idea of separation, solving by separation of variables, we're trying to get our y's on basically the left-hand side, x on the right-hand side, doesn't really matter the sides, this is just nice for solving it later. Then we integrate on both sides with respect to the same variable, hence x here. After that, if this is integrable function, we can do this, we can do this, we have an arbitrary constant, and this would be a solution to our differential equation. This is the whole plan. Now, do you guys want to see this in action, some actual examples here? I'm guessing that we do, because this is, well, it's clear to me, but hopefully it's clear to you. I know it's a little vague, though. We haven't really done anything yet. So, let's start. Any questions or anything at all? Okay. So first one. Let's look at dy dx equals y over x. You know, the first thing we got to do is make sure this fits our category. So let's see. Is it an equation? Oh yeah, clearly. Is it a differential equation? Is it a first order differential equation? What tells you it's a first order differential equation? Yeah, it's what type of derivative? Hence we have a first order differential equation. Is it variables that can be separated? Do we have a separable differential equation where we can get our x's on one side and our y's on the other side all by themselves? Yeah, very good. It's a product. Really, it's a product of a function of y times a function of x. If you think, well, wait a minute, that's a quotient. All quotients are kind of products, right? Because you just have y times 1 over x, and you have yourself a function of y times a function of x. Now, how would we get this to be the way that we want it? I want my y's on the left-hand side, I want my x's on the right-hand side. What do I have to do? If I divide by y, that would work just fine. So, dividing by y, I get 1 over y dy dx equals 1 over x. Not bad. Are all my functions of y on one side? And my function of x, that's on the other side, right? Now would be a perfect time to do what with this? Do you see why we have to have our integration techniques before we start this stuff? Because to undo a derivative, well, think about that. To undo a derivative, that's an antiderivative. That is the idea of an integral. So our separation variable works really nicely because when we separate our variables on both sides, we can integrate the left, we can integrate the right, and it undoes this derivative. This is the idea here. It basically gives us back the function we're looking for. Show of hands if you're okay with the basic idea. So let's integrate both sides. So if I integrate the left-hand side, it's going to be 1 over y dy dx. And then what goes over here? Remember all those times that your instructor said, you got to have the dx, you got to have the dy, you got to have all that stuff. You do have to have that. It's really not a trivial thing. You have to show me what you're doing, what you're integrating with respect to. Because when we do this here, we have to see that we've done the same thing on both sides of our equation. Otherwise, we mess our problem up. That's not fun to mess our problem up here. So what happens on the left-hand side? What are we going to have?
dx is canceled.
So we're going to have integral of 1 over y dy. We're going to have integral of 1 over x dx. Oh, this is interesting. 1 over y dy, 1 over x dx. Do we know how to do those integrals? Okay, everybody, what's the integral of 1 over y dy? Of what? Perfect. And what's the integral of 1 over x dx? Done? Why don't we have 2 plus c's? Shouldn't we have a plus c over here as well?
You can, but it just all goes together. And
That's right. If it's an arbitrary constant, it could be anything, right? So if I have a plus c from here, and I have a plus c from here, if I just subtract that, I'd still have a plus c. It'd still be some sort of a constant. A constant plus or minus another constant is a constant. You guys okay with that? You sure? I said a constant a whole bunch of times. So I'm going to put plus c, but I'm going to do this with it. I'm going to be a little bit special. The good special. I'm going to write plus c 1. And here's why we're going to do that. We're going to be manipulating this for a little while. And what we can do with our c here, the idea is, what we can do with that, we can change it around to make it, as long as it's still a constant value, whatever we basically want to, so it fits our solution better. So here's the things I'm going to do with this. The first thing I'm going to do, First, are you guys okay with this far? This is pretty straightforward, right? Kind of an easier one. First thing I'm going to do, I'm going to let C1 equal ln e to the C1. I want you to verify that that's actually possible. Do you remember that's possible? It's kind of an arbitrary thing, right? Any number equals ln of e to that number because ln and e, well, they simplify out. They're inverse functions of each other. Therefore, this would also equal C1. By definition, that happens. You guys okay with that one? Now, the reason why I'm doing this, I've got an ln here, right? I've got ln here, right? I don't have an ln here, but I want one. I want one because if I have one, then I can use e to the ln on both sides if I can combine these two things. So my plan is, well, if that doesn't have an ln, I'm going to make it have an ln. Then what I'm going to do is I'm going to combine these two ln's. After that, I'll have ln over here, I'll have ln over here. I can take e to both sides, well, both sides as an exponent on e, and get rid of my ln's. Does that make sense to you guys? So my plan is, I'm trying to put these two things together. Let's work with our constant in a certain way that we can do this. Now, in order to put these together a little bit further, I can't just have ln of e. I've got to have this absolute value up here too. So I'm going to put my absolute value here. Now you can notice that this is a true statement because e to any power is positive anyway. My absolute value is kind of trivial, but it's going to allow me to combine these two things. Show of hands if you feel okay with this one. You sure?
So this is the one spot you can't put plus c at the very, very end.
That's right. You kind of have to have breadcrumbs on what you've done with your constant. So some people do. Some people cheat and just go, plus c at the very, very end. But we have to really know what's going on here. Sometimes it really does matter. So this is like our breadcrumbs, what we've done to change our constant. Here, the hard part is honestly not the integrals. That's pretty easy. It's figuring how to put this constant in there so that we get one nice solution with one arbitrary constant. I'm going to do a couple of things with this. Are you okay with it? I don't really like the look of this. So here, this is things we can do too. I want to show you all this stuff. So you're like, oh, you can actually do it? Yeah, you can. Well, instead of having e to the c1, I'm going to let c2 equal e to the c1. I don't like this part of it. It looks really funny to me. And so here's the thing. You guys all agreed with this one, right? Well, c1 equals ln of e to the c1. Absolute value doesn't really make a difference. Is this still a constant? Is e to a constant still a constant number?
Yes.
Well, then I'm just going to call that a different constant. Notice how I'm using the subscript now of c2 to say, well, it's not, I don't want c, okay? Because c, that's what we're going to end with. We're going to end with the c. If I start with a c and end with a different c, it's going to look funny. So I call this c1 saying, hey, I'm going to change it, okay? I'm going to change it to a c2 saying, this is not my final c, but it still stands for a constant. Does that make sense to you guys? Are you sure? Okay, so then what happens is that c1 now would become ln absolute value of c2. This is what I want to use here. So ln absolute value of y, no problem. ln absolute value of x, no problem. Plus, what's c1? What am I going to use there? You are absolutely right. Sure. So we say, hey, c1? No, not so good. I need an ln. I also need absolute value, so let's change it. c1 becomes ln absolute value of e to the c1. No problem. Is this still a constant? Yeah, it's still a constant. No big deal. Is this a constant? Sure. Let's call it a different constant. We're saying, let's define c2 to be e to the c1. It's still a constant. We're fine as far as our notation goes. Therefore, c sub 1 equals ln of absolute value c sub 2. We're going to write that right here. The reason why we did this is, do you know how to put ln plus ln together?
Multiplication.
Yeah, very good. And since we have absolute value times absolute value, we get to multiply those things together. So this becomes ln absolute value of y equals, why don't you tell me what it is? ln,
Absolute value.
absolute value.
xc2.
xc2, okay, I like it. X times c2. We know that plus means a product within one ln. So two ln's being multiplied together, same base. We can, added together, we can multiply the product of these two arguments. Since they're absolute value, we make one absolute value out of it. Quick show of hands if you're okay with that one. I'm going to have to move over here. So now we have ln absolute value of y equals ln absolute value x times c sub 2. Can you tell me the next step that you guys would do if you had this problem? What would you do?
Multiply by e.
Say what now?
Move them up to the exponent of e.
Very good. We'll take this and treat them as exponents upon e on both sides of our equation. So, you know that's what you do, right? Every time you have ln on both sides, you go, wait a minute, I don't like ln on both sides. I want to do e to the ln of absolute value of y, and I want to do e to the ln of absolute value x plus c times c2. What happens to that? E to the ln, what happens? So we get
Absolute value of y.
absolute value y
Still.
still equals absolute value of x times c sub 2. Are we still okay with that one? Is this where I want to do? Yeah, this is where I want to do this. Now, I want you to think about something here. The definition of what absolute value actually means. I'm going to take a little sidestep so that hopefully you get the next part. If the absolute value of y equals x, what we end up getting is that y could equal positive x, or y could equal negative x. That's the definition of what absolute value is. It could equal absolute value equation is. So say, you know what, if you have an absolute value of something equal to a number here, or whatever, we can have, well, the inside could equal positive x, absolute value, keep it positive, we're done. Or, if we had negative x, absolute value of negative would change it to a positive. In either case, these would both be true. We get those two solutions for an absolute value. Should hands be okay with that one. We're going to write this just a little bit more simply then. So we would say y would equal positive or negative x. Does that notation work for you guys? Doesn't matter. It's absolute value. It says you can have either a positive or a negative, and that absolute value will keep that exactly the same, whether it's positive or negative. You guys with me? Using that logic over here, this lets us drop our absolute value. So what this says is, okay, well then, if I have absolute value of y equal absolute value of x times c2, we'd have y equals x times c2 for sure, but we could have positive or negative and it would still work for us. So if y can equal positive x or negative x, y here can equal positive x times c2 or negative x times c2. Show of hands if you're okay with that one. Are you sure?
And that would get rid of both sides of the...
That's right. That's right. When you're doing absolute value equations, we just need to treat one side as being positive or negative. There's really only two cases. There's the case where the signs are the same, both positive or both negative. Doesn't matter. The absolute value would change those negatives both into positives. Or the signs are different. One's positive, one's negative. Doesn't matter which side they are on. So we don't need all four cases, we just need two. Here's the two cases where they're both positive and or both negative, and where the signs are off by one. That's why we have the plus and we have the minus. That's a good question. Any other questions about that before we go on? You see, we're almost done. Very close to done. Because multiplication is commutative, we could do plus or minus c sub 2 times x. You with me? And here's the last thing. As soon as you get it down to here, where you have this nasty gobbledygook up here, this is what you define to be your arbitrary constant. See, here's the thing. If I have positive c sub 2, c sub 2 is a number, yes? It's a number like a 3, or I don't know what it is, but it's going to be some number. We could have positive c sub 2, or we could have negative c sub 2. Either way, this is going to be a constant value. Does that make sense to you? This is what we're going to define to be our c. So at this point we say, hey, let's let c equal plus or minus c sub 2. If we do that, that's an arbitrary constant. And what that is our solution to that particular differential equation. That's called a general solution because we have that one arbitrary constant. So we work with it, no problem. Get your variables on one side or the other. All y's, all x's. Integrate. That's how separation of variables works. Not a big deal. We all know how to integrate in this class. After that, it's really working to figure out how you get rid of ln, see if you can solve for y explicitly, and this is the plan for us. If you can solve for y explicitly, I expect you to do it. Can you always solve for y explicitly? No. Sometimes you can't. We're going to deal with a couple of those where you can't. I'll show you what to do in those cases. By show of hands, you feel okay with this idea. Feel okay with the constant? Usually for some people that really throws them for a loop, like what in the world are we doing? Well, honestly, it's dealing with a constant, making sure that you fit it into your equation so that you can solve for your y, so you can get your y by itself. As long as you don't make this into a variable or something, you'd be fine. So call this a different constant. Yeah, it's a little different. C2 equals e to the c1, no problem. Then we have all the way down to here, take that plus and minus with our C2, call that your constant, your arbitrary constant, and we solve our problem.
And we don't ever have to go back and substitute it and find C1 again after going through C2, C3, or however.
No, if you do it this way, if you do this correctly, even with initial value problems, you don't have to do that. This is why though you have to define it properly, because otherwise you're going to be off by some things sometimes. All right. So no, we typically don't have to go back and say what it was, but you should be writing this off to the side. Like I don't want you to go all the way down to here and then go okay, bam, and not show me any of this stuff, because that'd basically be impossible, right? To just arbitrarily call this something. But you got to define it somewhere on what you're doing with your C1 or C2. Can we try another example? You guys ready for it? Let's do this one. What you think? Separable? Non-separable?
It's non-separable.
You can
Is it a product of function of x times a times a function of y?
yes, there'd always be an extra.
You're the teacher, you tell me.
I'm the teacher trying to get you to understand. Is that the same as what I just wrote on the board?
Yes.
Is that a product of x times a function of y?
Yes.
Then that's a separable differential equation. Even though it looks bad, it's still a product of a function of x times a function of y. Get the y on one side and get the x's on the other side. What are we going to do here? So in our case, we'd have 1 over... I don't want to lose you on this stuff. Do you guys see how to make this into a separable differential equation? Just move right over. It's just a product. We have 1 over y dy dx equals x over x squared plus 1. And that's it. We okay with this one? Hello, yes, no? Are you sure? Do you guys see what I'm talking about being separable here? Separable means you get all the x's on one side and a function of y, all the y's on one side and a function of x on the other side. Sure you're okay with it? Let's keep going. What's our next step? Let's do it. Sure, let's integrate both sides. Not a big deal. We can totally do that. Can you do both integrals?
Yes.
Sure, this should be the easy part. My goodness, I'm not even kidding. This is like the easy part of doing this, not even a problem. Let's move a little quickly on this one. What's this integral, please? Ln what?
Absolute value of y.
Ah, very good. Can you do that integral?
Yeah.
Is it a trig sub?
No.
Make it easy on yourself. What is it? U sub. Absolutely a U sub. So U sub says that U would be what? Perfect. Du equals 2x dx. Du over 2 equals x dx. Hey, that's this right here. Not a problem. So this would become the integral.
What are they?
One happening.
1/2.
Okay, yes, very good. Okay, so 1 over u du over 2. See if I did that right. Did I do that right?
Yeah, you got it.
This is now our u. Okay, I got that one. x dx becomes d over 2, no problem. So 1/2 ln absolute value u. And now what?
Change it back to.
Got to change back to x. I'm going to do that right here. So 1/2 ln absolute value of x squared plus 1. Awesome. And then?
Plus C.
Sure.
C1.
Let's do C1. Yeah, let's do C1. Okay, need a show of hands, feel okay with that so far? Good, you should, right? Because these are some very basic integrals. Also, if you want to be a little fancy about this, and be like, well, you know what? I know that this has an ln, and I know that this has an ln, and this one doesn't. You can do things like this and go, let's just call this ln absolute value C1. Let's just do that. It's still a constant. You see what I'm talking about? You can do that if you want to. You go, okay, hey, it's plus some constant. I don't care what it is. You might do this if you want to be super notatious. I think I just made up a word. But super notatious about it, and just go, well, then call this C2 if you really must. Then C1 would equal ln absolute value of C2. Does that make sense to you? Then you'd say, okay, well, cool. You'd have your C1 initially. You'd say C1, C, is equal to ln of C2, second C. And then just call that, we got to make it.
Bless you.
No, it'll still be, oh, sure.
Too many
I messed
C's.
up that, didn't I?
C2 equal ln, or,
How did we do it the first time? This would be e to the
E
C1.
C2 equals E to the C1.
Yeah, C2 equals e to the C1. C1 equals ln.
Too many C's.
I know, C. Yeah. So we go, okay, C1 now equal ln absolute value C2. And you can define it that way if you want to. It's the same thing we've done before. Do I need to explain that further for you, or are you guys okay with that one? Honestly, I don't want to blow anybody out of the water right now. Honestly, are you okay with it? So you start with no, yes, no.
good.
Some people are no, but they don't want to admit it, because you're like, I have no idea what you're talking about right now. Let me go through it one more time. Do you understand that this integral is ln absolute value y?
Yes.
Do you understand that this integral, because we already did it, is 1/2 ln absolute value of x squared plus 1? Yes, no, yes,
Yes.
no, okay, okay. And what do you always put at the end of your integral?
C.
Only here you're going to define it a little bit differently. It's going to be c sub 1 because we will be changing it. How you define this, well, depends on what your equation looks like. If I have an ln here and I have an ln here, I'm probably going to want to combine this to one ln. If that's the case, then we need to go through that process and say, well, this is definitely equal to this. That's an arbitrary statement. If you let c sub 2 equal e to the c sub 1, then this piece fits here. C sub 1 equals ln absolute value c sub 2. And this substitution is what we would make for this C1. The only reason why we're doing this is so that we can fit our ln's together. So we can make this one expression in terms of a natural log, an argument of a natural log. Show of hands if that made a little bit more sense that time. Okay. So ln absolute value of y equals 1/2 ln absolute value of x squared plus 1 plus ln absolute value of c sub 2. Yeah, perfect. Now, there's one thing you got to know about combining logarithms and the order in which you do it. It's very important that you get this order. I know from your first test, some of you don't have this order down. Do I combine my natural logarithms right now?
No.
That's impossible. The reason is because, well, it's not just a natural log plus a natural log. It's 1/2 times a natural log plus a natural log. What do I need to do first? The half. The half's got to move. In order for you to combine these logarithms by a sum, so this plus here, this has to be gone. What's that become? So this would be a power of 1/2. What's a power of 1/2? That's a square root right there. So then we have ln absolute value y equals ln absolute value square root x squared plus 1 plus ln absolute value c sub 2. Now I'm going to have to move over here again. So, ln absolute value y, no problem. That's been there for a while now. Tell me what we get to do here. After we move up the 1/2, so 1/2 is a power, no problem. 1/2 has an exponent. Exponent of 1/2 is a square root. What do we get to do now?
Combine.
C2.
Because we defined this, we get to move our ln's together as one ln. So ln absolute value of what?
Times C2.
Time. Okay, very good. Make sure we don't do something silly here. Please don't do something silly here. Don't do something like this. Oh yeah, plus means plus. Yay. Don't do that. I'm begging you, please don't do that. Your ln rules say, no, plus product. And absolute value. Quick head nod if you're okay with that one so far. You sure? Okay, now what are we going to do? Come on, now what are we going to do? Think back to the last example. Now what are we going to do?
Raise both sides to e power?
Get rid of it.
Kind of, yes. Raise both sides as a power upon e. So we have these, we go, wait a minute. I know. As soon as I have an ln equal to an ln, this is a beautiful thing. This is exactly why we did all this stuff, is to get an ln equal to an ln. Because if I have that, I treat both of them as exponents of e. Nice. What happens when you take e to an ln power?
It's just
Everything magically disappears.
practically.
And this becomes absolute value of y equals absolute value of square root x squared plus 1 times c sub 2. Okay, show of hands if you can make it that far on your own. Feel okay about that one. Is it going to take you some practice?
Yes.
Yeah, probably. Is it making sense right now, though, for you?
Yes.
Are you sure? Are there any questions about this at all?
It always makes sense in class.
It does make sense in class, I know. Usually. Typically. I want to make sure that this does make sense for you, though, so I don't... Because if I'm losing you here, I'm going to lose you on the next stuff we're doing. I don't want to do that. You guys get the idea of changing your constant? How it doesn't really matter because we still have a constant. You call it whatever you want, right? You guys okay that we're doing that so that we can combine our ln's, yeah?
Yeah.
We're doing that because if you can combine your ln's to one ln and another ln, we treat those as an exponent of e on both sides, and we eliminate our ln. That's great. We have just the argument equals the argument, and now it's time to get rid of our absolute value. You don't stop here. You don't just drop your absolute value and call it c for some reason. You got to show me what you're doing, all right? So what we're doing here is we know that absolute value, by the definition I gave you over here, absolute value of y equals absolute value of something else is either plus this thing or minus this thing. Positive or negative would still give us the same answer because those absolute values will take care of those different cases for us. Where our signs are the same, both positive or negative, where our signs are different, one positive, one negative. Does that make sense to you?
See.
So think back to the last example we did, it's exactly the same. Now, last little bit, what are we going to do here? Because I don't like this. I don't like this at all. I don't like this. What are we going to do?
C equal plus
Give
minus
the
C2.
plus and minus to the c.
Okay, I can
Make
do that.
it c instead of c2.
So, plus or minus c sub 2 square root of x squared plus 1. No problem. I know how to do that. True or false? This right here, no matter what I give you, positive or negative and whatever c2 is, true or false, it will be a constant.
True.
Call that your arbitrary constant. So let c equal plus or minus c sub 2. Do you see, pun intended, why we use c1 to start with? Because we're going to end with a c. Does that make sense? If we use c here, this would be off. So we won't want to call it the same thing because it's not the same constant. It's a different constant. I don't care what it is because we can change this to whatever arbitrary constant we want to. So this could change to whatever arbitrary constant we want to. But it is a different technically constant. So we have y equals c square root x squared plus 1, and this is our general solution to our differential equation. Notice how general solutions have how many constants in them? One constant, because I can combine all of them. That's the idea. Show of hands, you feel okay with this one. We're going to start one more. I don't know how far we're going to get onto it, but I want to give you an example of an initial value problem, like a real one that you get beyond your Calculus 1 class. So let's solve this initial value differential equation and see how it differs a little bit from what we're doing. We'll see some of this stuff come into play. Okay. Looks kind of nasty. Let's see about this. What is this thing called?
Initial value.
Initial value. Do I use it here? This is basically used, look at the board, when you get to here. This is where you use it. You define all the stuff, all the C's and stuff, so that you can use it here without a problem. This is the idea, right? So, our plan for this problem, deal with your differential equation, make sure it's separable, make sure that you can actually do it, and then at the very end, we're going to use our initial value with it. So, we're going to ignore this for a second. We're going to look right here at this thing. Is that a separable differential equation?
Yes.
If you can make it to a product times a product, sorry, not a product times, that's silly. If you can make it a function of x times a function of y, or you can get all your x's on one side and all your y's on the other side and be able to do those integrals, then yes, that's separable. So, for us, let's start with, what would I do?
Move the y squared minus 1 to the right side.
I might choose to leave this
Oh,
one
wait.
on the left
No, I'm
for some
sorry.
So
reason.
I move that.
I might choose to move this one over. Very good. So we'd have y squared minus 1 dy equals, yeah, negative y e to the x dx. You guys okay with that one so far?
Yeah.
Furthermore, keep on going. What am I going to do now?
Divided by the negative y.
Yeah. So if I do that, or leave the negative, it doesn't really matter, as long as you get the y over here. In fact, I might choose to leave the negative on that side. What now? Yeah, you can move the dx. To be really proficient with our variables here and what our notation is, you can move your dx right here. Now, naturally, everybody's going to know that if you do that and you integrate, you're going to put a dx right back over here, right? And this dx will be gone. So if you don't want to show that, I don't know if I showed it on mine. Yeah, I did. I showed it because I'm really by the book on most of this stuff. So yeah, I would probably move this over here and show y squared minus 1 over y dy dx equals negative e to the x. Yes. Now we do what?
Integrate.
So if we do, we'll integrate with respect to dx, or sorry, with respect to x. We'll integrate with respect to the same thing. dx's are gone. Integral of y squared minus 1 over y dy equals integral negative e to the x dx. Let's keep on rolling. What are we going to do now?
Integrate.
Let's do the easy one first. Can you integrate this side? That's a piece of cake. What's the integral of negative e to the x dx? I love integrals of e to the x. So we know on our right-hand side, we're going to get negative e to the x. What's going to happen here? What is this? Well, how would you guys do this one? Don't make it harder than it is. U sub would not work. Y is on the denominator, it's not on the numerator.
Split it into two.
Split it into two fractions. Very good. Because if you do that, if you split this, then what this becomes is the integral of, look at this, look at, don't make it harder, make it easy. This is what you learned in Calculus 1 is to, if you don't know how to do it directly, you try to separate the fractions. This would be y minus 1 over y. You guys okay with what I'm doing there? Actually, what Charles was doing there, he says, hey, separate it. We got a numerator with 2 terms on it, denominator with 1. We can always separate that fraction, have y squared over y. Y squared over y is y. Minus 1 over y, minus 1 over y, no problem. Can you do that integral? Can you do this integral? Piece of cake. Let's do it together and then we'll come back to this problem in just a minute, okay? So, what's the integral of y?
Y squared over 2.
Minus. Perfect. Equals. We'll do one more step and we'll call it good, and then after that we'll, you know, we're almost. You guys want to hang out for like a minute? and finish this thing?
Yeah.
Okay.
Well, that's Bluetooth.
One thing that I'd probably do here, I'd probably multiply everything by 2. I'd do that to get rid of that 1/2, just to make it look nicer. So if I multiply everything by 2, we're going to get y squared minus 2 ln absolute value of y equals negative 2 e to the x plus 2 c1. I want to make sure you guys are good with that one. Are you good with that one? Sure you're good with that one? Okay, next thing we'd probably do, well, probably move that 2. So we'd get y squared minus ln of y squared equals negative 2 e to the x plus, here's where we start doing little substitutions. If you have 2c1, 2 times a constant is still a, if you want to define things like c2 equals 2 times c1, that's absolutely fine. Then this now becomes plus c2. So, integral, no problem. Integral, no problem, plus c1. Okay, cool. Multiply everything by 2, just to get rid of this fraction. We got y squared minus 2 ln y equals negative 2, and then plus 2c1. That 2c1, call that a different constant, just to make your life easier. Does it matter? Not really, but it makes your life easier later, because you don't have to worry about that too. So this now becomes c2. It's still a constant. Who cares about that? You guys okay with this one so far? Okay. Now, at this point, this is where you plug in your initial value. Notice, there's no freaking way in the world that you are going to get y by itself here. Do you see that? No, there's not all ln's. You can't get y explicitly. So this is where we use that initial value. We say y of 0 equals 1. Now tell me, what would our x become here?
1.
X. What would our x become?
0.
What would our y become?
1.
So if that's the case, we get 1 squared minus ln of 1 equals negative 2 e to the 0 plus c2. Plus c2. Show of hands feel okay with that so far. This is the easy part. This is really nice. How much is 1 squared?
1.
How much is ln of 1?
0.
Equals, how much is e to the 0?
1.
Times negative 2
Negative 2.
plus c2. And can I solve for c2?
Yeah.
See, the idea is, right now what we have here, look at the board, this is a general solution. If we called that c, we'd have a general solution to this differential equation. With an initial value problem, it says, okay, now find out how much the c is actually equal to. I don't care whether it's c1 or c2 or c3po. We're going to go ahead and plug, that was funny, we're going to plug that in, we're going to find out what it is. So we're going to have c2. I should have made a c3. That would be good. Do you understand that I don't care what c it is, whether I call this 2c1, it doesn't really matter. We're going to get the same exact thing here. c2, whatever you define that as, is going to be 3. What that means is that our specific solution, our particular solution to our given differential equation with our initial value is now that. That's the idea. So, we solve our differential equation just like normal, all the way down to where we have an arbitrary constant, just like always. Then we plug in our initial value, and we just use it. Solve for your c. As soon as you get your c, check it out. As soon as you get your c sub 2 or c sub whatever you have, that's what we put in that place. And now we have no arbitrary constant. We have our general, I'm sorry, we have a particular solution. Show of hands if you feel okay about that one.
Hey, okay.
All right, so let's continue. The last thing we're going to talk about in section 8.1 is natural growth and decay, and how this differential equation idea, at least by separation of variables, works for us. So, natural growth or decay, what we mean by that is either growth or decay at a rate that's proportional to the size of a given population. So, for instance, you can maybe think about this in terms of growing populations for bacteria, or people, or other species, or a decline of population, or like a half-life of substance. You guys know what half-life is, yeah?
Mm-hmm.
Half-life is substance. That's a natural growth and decay model. So we're going to study natural growth and decay. And again, what it means, it's a growth or decay at a rate that's proportional to the size of a population. And we're going to study all about this today. Now, when we talk about directly proportional, this is actually kind of an algebra idea. If we have something that is proportional, really what we have is y equals k times some variable. So if y stands for our population size and t is time, then our k is going to be some sort of a variation model. It's either going to grow this population or decline this population based on what we have for this. Does that make sense to you? So this is what directly proportional actually means. So y equals k times t means directly proportional. Well, if we were to take a derivative of this, here's what would happen. If we take a derivative and find out the rate of our growth or decay, so think about this. If this is our population, model, you guys with me on this? This is our population model. If we take a derivative gives us a rate of change. Does that make sense? You should learn that from your Calculus 1 class. Since a derivative is a rate of change, a derivative of a population would be how that population is growing, the change in our population. So if we take a derivative, we'd have dy dt, it would be respect to time, equals k times y, where y is a function of time. So this would be a derivative of, this would be a derivative of population with respect to time. So, we say, all right, cool. Here's our population with respect to time. If we take a derivative of this, we get the rate at which our population is changing with respect to time, whether it's growing, growth, or whether it's decaying, loss. Does that make sense to you? So we take a derivative, oh, cool. What we're going to get out of this is we're going to get some sort of a constant variation times y, where y is a function of t. Our population changes over time. So this would be the rate at which our population is changing. Now, what if k is positive? What's going to happen? Or is our population going to grow or decay? So for k is greater than 0, what this is going to be for us is going to be a population growth. Well, naturally, if k is less than 0, we're going to get decay. Now, I want to take a look at the model of this. What we're going to do right here is we're going to solve a differential equation once and for all for natural growth or decay. Would you like to do that rather than every single time? We're going to have a model for this, okay? So we're going to solve this model, and then I'm going to show you how to apply this to a variety of situations. So first things first. So let's say that we have this very basic differential equation that we started with right here. K times y. Well, that's this. What we know is that a derivative of y with respect to time right now, this is going to be the rate at which our population is changing, either growing or decreasing, decaying. Does that make sense to you guys? So we're going to start with this differential equation. Notice it is a differential equation, a first order differential equation, and, well, let's look at that. Is it separable? Yeah, we could get y's on one side, no problem. We can keep the k on one side and get the y on the other side. That would be not a problem at all. So it is separable. Also, what we're going to do is we're going to have some initial value. Here's what this is going to mean for us in terms of our population. Please listen carefully. I want to make sure that you guys all get this, because otherwise the next thing we're going to do is like, well, why are we doing this? What's this even for? Population is directly proportional to the size at some sort of, is directly proportional, and it's based on time. This is the rate of change of our population. We go, okay, cool, we got that. We get the rate of change of population. Our population has to start somewhere, doesn't it? So if this is population based on time, at time 0, we're going to have some sort of a starting population here. So we're not going to have negative time. Does negative time make sense to us? No. It makes sense, okay? Unless we go backwards in time, time travel, I don't know. We're not in physics class, so we're not going to talk about that here, okay? So what we have, unfortunately for some of you, I know, you're sad right now. For us right now, we're going to have a starting time of 0. Sure. At the starting time of 0, we are going to have some initial population. This is what this stands for. So this right here, for us, is going to be our starting population. Please keep that in mind when we're going through here, that y sub 0 is the starting population when t equals 0. So when t equals 0, that means when you start. It means no time has passed. Hey, when no time has passed, you are going to start with some amount of population, right? If you don't, otherwise your population can't grow. You have to start with something. Or it has to decay from somewhere. So this right here stands for a starting population. I was going to say one more thing, but I completely forgot about that. So initial value, starting population. Let's go ahead and let's see if we can solve this thing like we normally would. So remember how we solve any differential equation? The first thing that we do is we find our general solution. You guys remember that? With one arbitrary constant. We did that last time. And then what we do is we use our initial value to find a particular solution to this. Make sense? So right now we're going to take this off to this side. We're going to work just with this thing. So dy dt equals ky. At this point, you guys should be pretty good at doing this sort of thing. Why don't you tell me what I'm going to do here?
Move the y over.
Very good. Why?
You get your y's on one side.
Yeah, very good.
So it's in respect to line, and then take the integral and
So instead of having ky here, I want just the k on one side, I want just the y on the other side. So we'd have 1 over y dy dt equals k. So far so good? Hey, it's separable, let's separate the variables, no big deal. K is going to be, well, it's going to turn out that k is going to be something based on time as well. So we're going to integrate this with respect to time as well. So, well, now we did this last time. We said, okay, well, as soon as you have your variables separated, we take an integral with respect to whatever this thing is. So with respect to time here. So in our case, we'll have, all right, cool, integral of 1 over y dy dt equals integral of k dt. Okay, this should be pretty straightforward, but I want to make sure your brains are with it today. Show of hands if you feel okay with this so far. So we go, cool. Can we separate variables? Of course we can. Let's do it. Can we integrate? Of course we can. Let's do it to both sides with respect to the same exact variable. On this side, dt's are gone. We got integral of 1 over y dy. Tell me, everybody, what's the integral of 1 over y dy? You guys are on today. I like it.
Wednesday.
It's Wednesday. This is the only good day I get out of you. Awesome. Okay. Okay. How about the integral of k dt? You need to know that whenever we have, listen please, whenever we have a variable here that is not this variable, this is treated like a constant. I don't care what it is. Now k is a constant of variation, so this is cool for us. What's that going to be? Kt. Okay. Cool. So just like if we had 3, we'd pull the 3 out front, we'd have 3t. If we had k, we could pull that k out front. We have kt.
it's a constant.
It is a constant, yeah. Notice what's happening. Some of you guys were talking while I was saying this, but what you wouldn't do k squared over 2. Why not? Well,
It's a constant.
is that a t?
No.
No.
No, this is not the variable that we are integrating with respect to. It's treated as a constant. Is that clear for you? So we don't do k squared over 2. That doesn't make sense. We're integrating. This is why, ladies and gentlemen, your Calculus 1 teacher made sure that this is here. Then they go, that's not such a big deal. Don't worry about having the d whatever. It doesn't matter. Because then that would be like, well, what are you doing? Is k a variable? Is k not a variable? Does it matter? It matters. K is not a variable. K right here is treated as a constant. So we're not going to get k squared over 2, we're going to get kt. As if this was a constant because we treat it like a constant. Here, you could pull this out in front. It'd be basically the integral of dt. Integral of 1 dt is
T.
multiplied by the k, you get kt. Show of hands feel okay with that idea. Okay. Come on. Come on.
Plus.
Plus
C1.
C1. Yep. Plus C1. Okay, now, every time before when we had this was all like ln's, right? If it's not all ln's on this side, but it is ln over here, we can still do basically the same idea to get rid of this ln. We can take both of these sides as an exponent upon e. So I definitely want to get rid of the ln. Do you guys agree with that? I want to get y by itself. So that's our plan here. If we want to get y by itself, then we go, okay, well, cool. Let's take and make each side an exponent of e. We've done this before. This is not a big deal. So we have ln of absolute value y as an exponent. We have kt. Please notice something here real quick. This is very important that you see this. This whole thing is now the exponent. When you do this idea, the whole side becomes your exponent above your e. Like that. Quick head nod if you're okay with that one. Are you sure?
C.
Okay, now we're going to start working with this. E, ln, absolute value, what happens there?
Bye-bye.
That's great. This is very nice. So this is what?
Absolute value.
Yeah, that's right. Absolute value y.
But
Not a
we
problem.
did, we already said y is never going to be negative.
Made a mistake yesterday.
We're going to deal with that in a minute. It doesn't really matter, okay? Because we get to deal with it. Remember that plus or minus? That's where we get to deal with it. So, on the right-hand side, we're going to start manipulating this a little bit. Please remember our end goal. The end goal is cool. You got separation of variables. Do it. Do your integral. Have your plus, probably a C1, because we know this is not going to be our ending arbitrary constant. You with me? So we call it C1 or something. Get rid of any ln around your y, not a big deal. E, and then make each side an exponent upon e. You got it? Over here, cool, we still have absolute value y. Over here, well, this is funky. And so what I'm going to try to do is get rid of this plus c1. I'm going to try to change this into the arbitrary constant that I want and make it as nice as possible. So for us, I'm going to leave this e to the kt, but I'm going to multiply by e to the c1. I'm going to do that. Notice that if I have common bases, I can add exponents. Therefore, if I have a base with added exponents, I can separate into multiplication of common bases. You okay with that one? Well, that's kind of nice. Now, at this point, let's do a little razzle-dazzle. This is a constant, true?
Yeah.
Is this a constant? Let's call this a constant then. So we're going to make a little side note. E to the c1 is now going to be equal to c2, our second form of our constant. Does that make sense? So here's our first one. We go, no. Let's split this off. Because if I can split this off, this is nice to get rid of this thing, right? So, hey, that's still a constant. This is e to the c, no problem. That's still a constant. Let's call it just a different constant. Well, now we have absolute value of y equals, I'm going to move this to the front. This will be c sub 2 times e to the kt. That's an awful k. E to the kt. Okay, show of hands if you feel okay with this so far. We've done it before, I just want to make sure that you guys are with it. Now, there's one more problem that we have here to face. What is it?
The absolute value.
Yes, right. We need to get rid of that thing. And we've learned before that if we have the absolute value equal to some sort of an expression over here, that what we can do to drop our absolute value is just consider that absolute value would take a positive expression or a negative expression and make it true. So for us, we have positive or negative c sub 2 e to the kt. And there was one more little caveat that we could do here. The idea was, hey, that's a constant, right? That means this thing is a constant. Call it a different constant. Now, this thing, is a positive or negative c sub 2 still a constant?
Yes.
This becomes our arbitrary constant. So now we're going to let c equal plus or minus c sub 2. And we get y equals c e to the kt. Okay, I want to show if you guys feel okay with that so far. So let's go through maybe a 20-second recap real quick to make sure that we are all with it. First thing we got is this. We know this means directly proportional. We know that this means the rate of change of whatever we're talking about. In this case, it's population. So okay, we have the rate of change of our population. We know that that's a differential equation which we can solve. We just solved that differential equation. It's right here. We just solved it. This would be called my general solution to this differential equation. If this was not here, I would be completely done. Does that make sense to you? Now, we also know that initial values are going to give us a particular solution. So, differential equation, no problem. Without this, we're done. We got a general solution. This is basically a family of curves. You with me? Mm-hmm. Now, to get a specific curve, to get a particular value, we need an initial value. That's what this thing is. So, general solution, very good, has one arbitrary constant. That's an arbitrary constant, that's c. K is going to be based on whatever your population model is, okay? So that's not arbitrary. C is your arbitrary constant. Now, to get our particular solution, we're going to now use our starting population, or our initial value in this case. So, let's use it. Our initial value, if you didn't catch it, our initial value is our starting population. It says, hey, how much is your population at time equals 0? Or so basically when you start your experiment, or when you start your research, or whatever you're talking about. So it says, what's going to go in place of our, now we don't have x's here, okay? We have the variable of what? T's are variable, and y. So what's going to go in place of our t?
0.
Good. What's going to go in place of our y?
Why not?
Y sub 0, that's right. Did I add? Why not? Hey, why not? Yeah, so what we do here is we go, okay, well, this says, remember that y is a function of t. We said it right here. Y is a function of t. So when I have y of 0, it means that, well, c is still there, e is still there, k is still there, but t becomes 0. Now it says y, when I plug in 0, is going to give me y sub 0. Well, this y is then y sub 0. Quick show hands feel okay with that so far. Now this is going to be kind of interesting. Now hopefully it makes sense that we're going to get not an actual number for c, because we don't have an actual number here. Does that make sense to you? I'll explain this in just a bit so it makes it absolute perfect concrete sense for you. What's going to happen to our e to the k times 0? How much is that going to be?
1.
So this is 0, e to the 0 is 1. Therefore, what we get is y sub 0 equals c. Y sub 0 equals c. Does that make sense? Let's go one step further. We're going to finish this thing off. So, for the last time, hopefully, general differential equation, not a problem. If I have an initial value, I can get a particular solution. Our particular solution, therefore, is y equals, what did our c change to?
Y sub 0.
All the way down.
Why?
What's our c?
Why not?
Let's talk about what this actually means. Let's talk about what this means. Did you all understand that y sub 0 equals, y of 0 equals y sub 0 is your starting population? Please listen up here for a second. Let's say that your starting population was, I don't know, 200 whatever, 200 units, people, whatever you're talking about. So at time 0, you'd have 200. Does that make sense?
Yeah.
Over here, you wouldn't have y of 0 equals y sub 0. You'd have y of 0 equals 200. Your c would equal 200 here. Does that make sense? This would be 200. Y sub 0 stands for your starting population. So what's nice about doing it this way, what's nice about solving this once and for all, is that now we have a model for growth or decay based on your starting population. Please keep in mind that Y sub 0 is your starting population.
What was that? P-E-R-T.
It's really similar, and that's very, very interesting because we get that growth of interest, the amount of interest that you earn. What is it? It's amount, isn't it? Equals the
Amount.
principal e to the rate times time. Very interesting that we get it from here. But yeah, that's where it comes from. So what this is this is a solution for growth or decay, where Y sub 0 is our starting population. What that means is that anytime you want to find out how your population is growing or decaying, you can use this model right now. We did it, right? We said, hey, if it's directly proportional to the size, the rate of change equals this. Not a problem. We solved our differential equation generally. We said, now, let's consider that at time 0 we have a starting population. If we use the time 0 equals a starting population, then C actually equals that starting population. This is all I'm trying to say, is that our constant, our arbitrary constant, is actually equal to the starting population. That's what I'm trying to say here. What that means is that this guy right here is basically a solution for growth or decay, where Y sub 0 is a starting population. Talk about a couple other things. I mentioned it over here, but I want to give you a picture of it. Let's say that K is positive. If K is positive, understand a couple things about this. Y sub 0 is a constant. Do you understand that? It's going to be a number here. So it's going to be whatever you're starting with. It's not a variable. It's going to be like in this classroom we start with, that's a weird talk about growth. I don't want to talk about decay either. I don't want you all to die or anything. Let's say that we have a culture of bacteria, okay? It's going to start somewhere at a finite number. That's going to go here. So notice, that's a constant, but this is e to some variable. It's an exponential based on e. Well, if that's the case, t is always going to be what? Positive or negative?
Positive.
For sure, we're not going to go backwards in time. So k is the only thing that's going to determine how this graph looks. If k is positive, it's got to grow because it is an e, a function of e to some power. Do you remember how e looks? It's the, remember that? So it's going to do this. Now, of course for us, if this is based on time, what part of this graph is not valid? This doesn't matter, because we can't have negative time. We're starting at 0. So this is what it says. That hopefully this makes sense to you. It says you're going to start somewhere. Hey, look at that. You're going to start at 0. You'd start at the starting point. Why? That makes perfect sense. That's our population size right there. It says that if k is positive, you will be growing at some rate. Exponentially, yes. That's how growth works if you think about it. You start with 2 bunnies. A lot of bunnies. Okay, give it a year. It produces as much meat as a cow. Okay, if you have 2 bunnies, you just let them go. And do whatever bunnies do. Now, if k is negative, we get that other graph. This one. Again, for the same reason, because this is a function of t, and t cannot be negative, that side doesn't matter. Well, this would be what? Growth or decay? Actually decay. You're going to start somewhere. Hey, look at that. If you plug in 0, you're still going to get y sub 0. Your population starts somewhere, only now it's declining. Does that make sense to you?
Yeah.
Show of hands feel okay with this idea. Cool. Would you like some examples of how to actually do this? Question?
That was the proof, right?
This is a proof that we can do natural growth or decay with this model. That's basically what that's saying. I'm basically saying, hey, you know what? If I get to tell you that our population is growing or declining, or find out what your population is doing, you can use this with your starting population. Now we're going to talk about some very simple examples and build on this right now. That was a good question. Any other questions at all? Did this side make sense to you? Because I got to erase this before I keep going. Okay. one thing that does have to be present is you do have to have this idea of proportional growth. If the problem doesn't state that, then you can't really assume it. So this is all based on the idea that the population is growing or decaying at the in proportionality to the starting population or to the population. Does that make sense? Some things grow or decay outside of proportion to the population. For instance, I'm not sure if this is exactly true, but I would think it would be true. If you have a series of bacteria and you drop some acid onto it, it's probably going to die very, very quickly, not proportional to its size. That's going to be an outside cause. It's caused it done. Does that make sense? Or an antibiotic or something. So that would be non-proportional to the size. It's just going to kill it all in a matter of seconds, whether it's 5 bacteria or a billion bacteria. You just dump it on there and it's gone. Does that make sense? So what we have to state on here for us to do this, your problem has to be worded something like this. Growth of bacteria is proportional to the population. It's got to say something about the proportionality of growth or decay. Okie dokie? Growth of bacteria is proportional to its population. And the reason why it has to be is because this right here, this comes from the idea of that directly proportional model. So we have to have that somewhere worded where it's proportional. Initially, (600) bacteria are present. After 3 hours, 10,000 bacteria are present.
Okay.
You ever done any work in algebra with direct variation or inverse variation? You know that you basically have to be given two things. You got to be given a formula, which we have. You got to be given a scenario, like after this amount of time, this is happening. So in order for us to find k, this would have to be the case. So you'd say, okay, what's the starting size? Let's give some time and say, oh, now it's here. Now we have some sort of a model to base this growth on. Does that make sense to you? So here's what we're going to do. What I want to do is find the amount of bacteria after t hours. Find number of bacteria after t hours. You see, if we can do this, if we can find it after t hours, then we can plug in however many hours we want, and we'll be able to find a good model for our bacteria. So far, so good?
Yeah.
Basically, what you said is right. We're going to be finding k here. We got to find that variation, that constant variation for this particular model. So, oh, man, what are we going to do? Well, do we have a model for growth or decay that's based on proportionality to a population? Yeah, we actually did it. Don't redo all this stuff. Okay, I did this for a reason, so that we understand that that's okay. So we have, all right, well, this is very convenient for us. We know that y equals y sub 0 e to the k t. We know that's true. We also know something right off the bat. Right off the bat, we know one of these pieces. What one of these pieces do we know?
What's the time and initial?
Initial and final.
We know initial. So initial says, hey, y sub 0 is how much?
600.
That's right. That's always, this is what I was trying to get at you here, is that your arbitrary constant is here, as we showed it, proved it. Y sub 0 is your initial population, which makes it really nice, because right off the bat you go, okay, how much did you start with? You started with 600. Your initial value is, at time 0, it is the 600 units of bacteria. Okay, show of hands, you feel okay with that one. It's kind of simple, but I want to make sure that you actually get it. Next up, what do we know?
Time.
What do you mean?
The T.
Times three.
Times.
What's our time?
3 hours,
And what do we have after 3 hours?
10,000
10,000 what?
bacteria.
And that's a population. So if y is our population variable, then y, when I plug in 3 hours, is equal to how much? Do you notice how I'm creating another type of, it's not an initial value, but it's another, it's basically an ordered pair. It says when you have t of 3, you get y equals 10,000. This is what this second sentence basically tells us. Should eventually be okay with that one. Let's plug the numbers in. So we had our initial 600 units of bacteria at time equals 0. Well, that's not bad. That's pretty easy to actually do. You can think about it. You could plug in 0 and 600. You solve for y not every single time, couldn't you? Even if you didn't have this, you could do that. You could say, hey, when t equals 0, this is gone, correct? And y would equal 600. Hey, y sub 0 equals 600. Duh. That's a piece of cake. We just did it once and for all. That's why it was so easy over here. Now, when t equals 3, after 3 hours, we have 10,000 units of bacteria. So what goes where?
10,000?
10,000 goes here?
No.
10,000 goes here?
Yes.
600 is not going to change. E to the
3K or K3.
k times 3. So y was 10,000, no problem. This is how this works here. This is how ordered pair works. It says this goes for your y, this goes for your other independent variable of t. Your k is what we're looking for. How am I going to do that?
Divide by 600 to
I would
get
do
back
that.
the log.
I would divide by 600. So if I divide by 6, what am I going to get if I divide by 600?
100 over 6.
Say what now?
Let's see,
100. Let's try to simplify.
Uh-oh.
50 over 3 maybe?
16.67.
like fractions.
So 50 over 3 equals e to the k times 3. Show of hands if you're okay with that one. Now tell you what, we're going to be smart about this. Hopefully we're going to be smart about this. I'm not going to do an ln on both sides. I'm not going to do that. I know there's an e right there, but I'm going to be smart about this. Here's what I'm going to do. What I'm going to do is I'm going to actually make this so instead of getting k itself, all I really need is to substitute for a part of this, right? Just a part of it. I just need not just the k, but maybe if we can get rid of the whole e to the k, that would be kind of nice. Wouldn't that be kind of nice? So I'm not going to solve for k. I'm going to solve for e to the k. What that means is that if I have e to the k times 3, what if I take that to a 1/3 power? I do that on both sides. Is this 1/3 going to get rid of this 3? We have exponents raised to exponents, we multiply, yes?
Yeah.
Yes.
This is gone. So what this says is 50 over 3 to the 1/3 power is equal to e to the k. Now that is a good substitution. This is what we can put in right here. Now that's a problem. I'm not going to do parentheses, that would be mathematical error. But this is what we're going to be doing here. Show of hands if you're okay with that one. So we haven't solved for k. We've solved for e to the k, no problem. Just let that be our substitution. Does that make sense to you? Okay, so let's do it. I'm going to change this around just a little bit so that we see what's going on. This would be y equals 600 e to the k times t. Or if you thought about it differently, this would be y equals 600 e to the k to the t power. You guys okay with that one? Am I going too fast for you, or are we okay? It's just some algebra, but I know that algebra can be intimidating for some of us. Okay, well, then y equals 600. Do we have an expression that's equal to e to the k? How much is it?
50 over 3 to the 1/3 power.
Let's be real careful about this. That's all being raised to the t. You guys with me on that one?
Mm-hmm.
So we said, all right, cool. We have this piece of cake. We have this will let us solve for our k if we wanted to. We're smarter than that. You know, okay, I could solve for my k right now if I want with an ln, no big deal. Or I could think about, well, let's make things a little bit nicer. Let's just solve for e to the k and use that substitution. So are you okay solving for e to the k here with that 1/3 power? Well, now we go, all right, well, let's think about this. This is really 600 e to the k all to the t. Since e to the k equals 50 over 3 to the 1/3 power, e to the k equals 50 over 3 to the 1/3 power, but this is raised to the t, therefore this is raised to the t power. You follow? One last thing we're going to do. This is nasty. Exponent raised to it, that's nasty even the way it's written. You're going to make that better. I find my handwriting is getting worse and worse as I get older, and that's not cool. My written, like on my note, it's perfect. But on the board, I keep going faster and faster, it gets sloppier and sloppier, so I gotta stop that. Make a mental note to stop that. Exponent raised to an exponent, what do? Let's put that together. Let's have y equals 650 over 3 to the what power?
T over 3.
T over 3, that's perfect. 1/3 t or t over 3, that's fantastic. Now here's my question. Is this going to be the growth model for everything in the world?
No.
This is only for this specific type of bacteria. And we got that because we had initial population, we had to have that. And we had to have how it's actually growing. How it's growing lets us make this model for it. So far, so good? But now that we have this, I can ask you any question that I want to. For instance, can I ask you how much bacteria will be present after 5 hours?
Yes.
Sure. Let's figure that out. How much bacteria will be present after 5 hours? How much bacteria present after 5 hours? Where would the 5 go here?
T.
There's only two places to plug numbers in, isn't it? The T stands for your time. What's the Y stand for?
Your amount, your end.
That's very good. Your population, no matter what, stands for your population. So population size and your time. So if I want after 5 hours, our population would equal a starting population of 600 times 50 over 3 to the 5/3. So we do 50 divided by 3, take it to the 5/3 power, then multiply by 600 by order operations. Make sure you do it in that order. And Y would equal what?
You said that so
I
fast.
got 65,247.8.
Same here. Same here.
I have no idea.
Wait.
What'd you say it was?
65,247.8.
Let's just call it 248.
6.5 times 10 to the 4th.
65,248. About.
100 degrees.
About 65,248. 65,248 what?
Bacteria.
Little bitty bacteria. That's right. Now, I'm no scientist. I'm really not. I'm not very good at science. Actually, I was decent at science. But let's just pretend for a second that it takes 20,000 bacteria to make you sick, or so you present symptoms. So you get this little infection of 600 bacteria, and after 5 hours, you get 65,000 bacteria. Are you going to start feeling symptoms if the symptoms start, at 40,000? Yeah, okay. You're gonna start feeling symptoms. I don't know if that's the way it works, but I'm going to pretend it does in my little mind. That makes sense to me. But anyway, no matter what, we can find out a growth model for this particular bacteria. Does that make sense? Until the food runs out. Once food runs out, well, then naturally it's going to start decaying. Okay, last question. Could you find out how long it would take to grow bacteria to a certain size?
Yeah.
Let's find that one out. So, what do I want? When will the bacteria bacteria reach a population size of 24,000? Maybe this is the better question. It says, okay, tell you what, we know with this strain of bacteria that you start feeling symptomatic at when the bacteria is over 24,000 units or whatever. We started at 600 units. So right now we need to figure out, well, when's it going to reach that? How long does it take for you to start feeling, or whatever we're talking about? How long does it take for it to reach that population, no matter what we're talking about? Where would the 24,000 go?
Why?
So we'd say, from our model here, this is what we can use in either situation. We'll ask two questions. How much is it going to be after a certain time, or when's this time is going to be a certain amount. So 24,000 equals 600, oh, I give you nice numbers, 50 over 3 to the t over 3. My goodness, how in the world would you solve that? Yeah, I'd divide by 600 to start with. So we'd get how much? 40?
4.
40.
40.
Yeah, 40. Well, there's really no way around it here. What are we going to do?
Natural log.
Now it's a natural log of both sides, because we got to get to this exponent. So natural log of 40 equals natural log of a bunch of crap. Why we do this, I'm not going to teach you the algebra again. Why we do this is so that we can bring the exponent down. If we do that, ln of 40 equals t over 3 ln 50 over 30. After that, can you solve for your t?
Yes.
This would be multiplying by 3 and dividing by ln of 50 over 3. So 3 ln 40 divided by ln of 50 over 3 equals t. Now I've done the work for you already, so if you want to practice with your calculator, go ahead and do that right now. But for us, we're going to get t is approximately 3.93 hours. Let's see if that jives with our initial conditions over here, okay? If it says 600 present after 3 hours we get 10,000, does it make sense that after 3.9 hours we get more than that? Yeah, it's exponential growth, so it's going to grow faster than linear. So it is growing like this, okay? The more bacteria you have, the faster it's growing. That should make sense. Bacteria doubles pretty quickly, okay? So you get more bacteria, it's going to grow faster in proportion to its size. Show of hands, feel all right with that one? Tell you what, we'll start one more now that we have this idea kind of down. It goes so nice and quick for us. Let's talk about something a little different than growth. Let's talk about decay. Are there any questions on this at all? Did I
Yeah.
explain it well enough for you to understand it?
I just got one question.
Question.
Because when we were solving for K, we solved for EK instead, so it's fine.
Yeah.
Just solve for EK.
Yeah, I would definitely solve for e to the k because we're just taking that little bit and substituting in there, okay? You could actually solve for k, but then when you realize it, it's going to be e to the ln, isn't it?
Yeah.
E to the ln is gone. So we're going to be smart about this and not have to do that. Here, there's no way around it. You got to solve for t itself because we want to find out the number of years. Okay, have we explained this well enough for you? Okay. One thing, I think I introduced this section with this. One thing that decays in proportion to its population are certain substances. So let's assume that the half-life of a substance is proportional to its, the way that this decays is proportional to its size. So suppose that the half-life of some substance, of compound A, is 1,602 years. Let's suppose that we have 100 milligrams to start. Almost sounds like science, doesn't it?
I'm like, it's chemistry all over again.
Well, is this organic chemistry or something?
No,
Just regular chemistry?
it's 4B.
4B.
I don't even know what that means. Let's find the amount. You're going to notice that what we do for decay, what we do here, is very akin to what we did for growth. We're going to follow the same exact model. We're going to find the amount after t years. Well, that should be pretty easy to do. Let's start. Find the amount after t years. Do we know that this is growth or decay? Yeah, it's decay. Well, the model's going to be exactly the same, so we're going to have y equals y sub 0 e to the k times t. Now, there's a couple things that we need to know about this. Firstly, do we know how much y of 0 is?
100 milligrams?
Remember, y of 0 says how much do you start with? Do you know how much you started with? You guys okay with that one? You start with 100, hey, y of 0 or y sub 0 is going to be 100. We know that one. But there's also something else. We just need to know how to write it. When it says a half-life, it gives us a piece of information here. So it says, after how many years?
1602.
After 1602 years, we're going to have half, please listen carefully, we're going to have half of whatever we started with. Does that make sense? So we're going to use our starting amount to come up with this thing. If we start with 100 milligrams at year 0, I say, let's give it 1602 years. We're going to have, that's what half-life means. It means you have half of it left. How much is going to be left?
50 milligrams.
If you get this, you're going to get the rest of this. Show of hands if you get that one. Tell you what, why don't you try this one? I'm going to go through this quickly next time, very quickly next time. Why don't you try this at home, or if you're watching this, try this on your own. Find out a couple things. Firstly, I want you to find out how much is after t years. So go up and do this. Basically, you can get down to this far, okay? After that, find out how much you'd have after 1,000 years, and how long it would take to get 40 milligrams. So basically, do you see the similarity here?
Yeah.
It's exactly the same. I'm not asking you to go out and solve how to get to the moon or something. Actually, that's already been done a long time ago. Unless you're a conspiracy theorist and they never made it, whatever. So, after a certain amount of years, after a certain amount of years, this can be very similar. Let's just plug the number in. How much will we get to, or how long will it take to get to 40 milligrams? So, after 1,000 years, how much we're going to have, and how long will it take to get to 40 milligrams? Can you guys do that for me? Let's do that. 1,000 years. How long will it take to get 40 milligrams? Okay, let's go. So we have this problem we're working on. As I've asked you to go do this on your own. Most of you didn't actually do that. Probably people on tape didn't do that either, so we're going to do it together. But very fast. So the half-life of some substances is 1,602 years. If you have 100 milligrams to start with, a couple questions. Firstly, find the amount after t years. Now, what we're going to assume is that this fits our model of y equals y sub 0 e to the kt. If you'll remember from last time, we got this from solving basically just solving a differential equation. That was it. This was a proportional problem that we said, okay, if we find a derivative, that's a rate at which this is changing. Therefore, we solve a differential equation, and we have one situation that let us go from an arbitrary constant into this y sub 0, and it was that we are always going to start with some initial amount when we're checking population growth or decay. Here, our population is kind of like this 100 milligrams of some substance that we have. So, with our half-life, the first idea is, well, you got to see what our y sub 0 is, and then we're going to have to see something that lets us solve for our k. So, firstly, tell me what the y sub 0 stands for.
Initial.
Sure, initial population, or initial amount that we have. What is our initial amount that we have?
100 milligrams.
Okay, so what we know that right now is that y sub 0, because we are in terms of t stands for, in this case, it stands for years. It can be any amount of time, minutes, hours, whatever, seconds sometimes for certain half-lives. But here we have, well, y sub 0 equals 100. Well, yes, it is 100. Y sub 0 stands for the amount that we're going to have after 0 years have passed. So basically, right when we start, we have 100 milligrams of some substance. Now, what's interesting, this is, I think, where I probably left you last time, I'm not really sure. We also have another statement given up here. If we know that the half-life is a certain number of years, then what we know is that after that amount of years, specifically here, after 1,602 years, we're going to have half of whatever we started with. What that does, that gives us another ordered pair. It says after this amount of time, you should be able to tell me how much we have left. How much are we going to have left?
50.
How'd you get 50?
Half of 100.
Yeah, it's half of 100. If the half-life is 1,600 years, then after 1,602 years, we're going to have half of our initial amount, or half of the 100, that's the 50. Show of hands, feel okay with that so far? Well, now we start breaking it down. Okay, so if y of 0 is 100, that means that our starting amount is simply 100. Therefore, instead of y equals y sub 0, we go, no. Our starting amount is 100 milligrams. Not a problem. Now what are we going to do? Sit here quietly. Very good. That's exactly right. What are we going to do?
Change the d by 9, which is 1,602.
What's the idea in plugging those numbers in? What are we trying to find right now?
EK.
We can solve for k. But
EK.
yeah, we can solve for k. But a nice thing about this is that if we solve for e to the k, well, then we can make a larger substitution and not have to worry about the ln. So what we're going to do is we're going to try to find a value for e to the k. How we do that? We use this other piece of information. We have to have two pieces. You've got to have an initial value, then we have to have how much you have left after a certain amount of time. You've got to have another ordered pair, something that tells you something additionally. So in our case, we go, all right, no, not a problem. How much is the y if I plug in this? Is it the 1602 or is it the 50?
50.
Yeah, it says the y is the 50. That's how much we'll have left. The 100 doesn't change. The e doesn't change. The k is what we're really missing here. Times, what's the t in our case?
1602.
That's right. What's the next thing you do?
Try to isolate e to the k.
Sure. How are we going to isolate e to the k? Come on, help me out.
Divide by 100.
If we divide by that 100, we're going to get 1/2 equals e to the k times 1602. Keep writing 1620. 1602. How about after that? Can we solve for e to the k in this case? Of course we can. Yeah. If we consider this as 1/2 equals e to the k to the 1602 power, well then basically all we got to do is raise both sides to a specific value that's going to give us a simplification of that exponent. Specifically, if we take both sides to the 1 over 1602 power, it's a weird power, but if we do that on both sides, then what we end up getting is that e to the k equals 1/2 to the 1 over 1600 second power. This right here, do you remember that when you have exponents to raise to exponents, we multiply? 1600 times 1 over 1600, gone. We just get e to the k. This side we have 1/2 to the 1 over 1600 second power. Show of hands, feel okay with that so far? I know we went through a little fast, but we've done this before, so I want to make sure that we get on another concept here just a bit. Oh, don't want to erase that. Almost did. Well, now we can do our substitution. So when we do, notice that we want to change this thing, but we only want to change the e to the k. So we'll have y equals 100. How much does the e to the k become?
1/2 over 602 power.
Is that it?
Times
T.
t.
Where's the t go?
And the exponent.
Okay, so really, this is normally like this, correct? This would be, oh, look at this, 100 e to the k. No, not e to the k. We're going to have 1/2 to the 1 over 1602 power to the t, or times the t. So we could have to the t power, but to make it a little nicer, we just have to multiply this power times t. To make it a little nicer than that, well, instead of having 1 over 1602 times t, let's just put the t on the numerator. That'll make it a little bit nicer. So we have that. I want to show if hands you feel okay with that one so far. Now, this is basically all we have to do to satisfy this question. Find the amount after t years, we've done it. Y stands for the amount of the substance we have left when it's based on however many years we're given. Does that make sense? This half is not coincidental. If you're talking about half-life, well, think about that. If you're talking about half-life, whatever you have here should be exactly half of whatever you have here, correct? And your very first step is going to be to divide. You're always going to get 1/2 right there. It's basically just based on whatever the number of years is, where you start with, whatever the number of years is. Show of hands feel okay with that idea. Now let's solve our questions. If I want to find the amount after 1,000 years, use our model. Where's the 1,000 go?
And T.
So we're going to have y equals 100 doesn't change, 1/2 doesn't change. We're going to have 1,000 over 1,602. And someone who's really quick with a calculator,
64.88 milligrams.
64 point what?
88.
Sure. 64.8. That sounds about right. Let's see if that sounds about right. What we know is this. We know that half of this material should be gone after 1,602 years, correct? So if I give you 1,000 years, less than 1,602, we should have less than half of it gone. Does that work out for us? We start with 100. If we do this and we get something like 300, your product has miraculously grown. That probably won't make sense, okay? This is supposed to decompose over time. So this is less than halfway gone. We've had less than half the half-life, so sounds about right. How long will it take to get 40 milligrams? So what would we do in that case?
Make y 20.
Yeah. In this case, we say, all right, we'll use our model here. If y stands for the amount of the substance left, then we're going to have 40 milligrams equals, well, the same model. 100, 1/2 to the t over 1,602. How would you solve this? What would you do?
Divide by 100 first.
You divide by 100. So if we divide by 100, we get 4/10, we get 2/5.
2/5.
Now at this point, yeah, we should probably take the natural log. If we do that, what we're going to be allowed to do is take the exponent and we're going to move that forward. So natural log of 2/5 equals natural log of 1/2 to the t over 1,602. After that, well, we should know this. The reason why we do a natural log with exponentials is this allows us to move our exponents to the front and the coefficient. So we have ln of 2/5 equals t over 1,602 times ln of 1/2. Now we just do some multiplication and division. If we want to solve for t, we're going to multiply by 1,602. We're going to divide by ln of 1/2. So we get 1,602 times ln of 2/5 over ln of 1/2 equals t. Has anyone figured that one out?
2,118 years.
2000, let me see if that's what I got too. Yeah, that's exactly what I got. 2,118 years. Let's see if that fits our model. Half of it should be gone in 1,600 years, correct? We're asking when's more than half of it going to be gone? Well, it should be more than 1,600 years. We got that. It's not like hugely more, like 1,000,000 years or something, but a few hundred years later. Exactly right. Show of hands, feel okay with this idea. Pretty straightforward. Actually, we didn't even do calculus today, did we?
No.
It's basically just plugging numbers in and solving for them. That's really just the idea. Any questions or comments before we get on to our last one? You sure? Okay, last one. This is an interesting one. I like this question, this idea. Because I've always wondered about it when I was a kid, why this works the way that it works. What I'm talking about is the law of cooling. By the way, any questions?
The law of what?
The law of cooling. The law of cooling.
Are we going to apply calculus to any of this at some point?
This is calculus. We've already done it.
Yeah, well, I just need more.
No.
Okay.
No, not really. I just want to show you a few applications of what this can be used for. I think I've basically covered how to do differential equations by separation of variables, right? It's a very straightforward idea. We're not going to sit there and do tons of examples of that. I wanted to give you something more concrete. So I'm trying to give you some. I find these interesting. I really do. That this is applicable. Yeah, we're not doing a whole lot of integrals right here, but we've already done the basic integral to solve for population growth or decay. So we're just using that right now. One way that we can use that is with this law of cooling. Now, what happens if your house is 50 degrees versus when your house is 90 degrees? You take something out of the oven. In which case is that thing in the oven going to retain its temperature longer?
90 degrees.
obviously, because the surrounding ambient temperature is warmer, right? Well, there's actually a law for that. It's called the law of cooling. Now, I didn't understand that when I was a kid. And I didn't understand why sometimes when you take cookies out of the oven and it's 85, they burn your mouth for like 30 minutes versus in the wintertime you can eat them in 5 minutes. I didn't get that. So I always, when I saw it, I'm like, oh yeah, that makes perfect sense now. Because I'm an idiot when I was a little kid. I burned my mouth all the time. Because I was a fat kid and I couldn't wait for them to get out of the I was eat them all. Anyway, so, law of cooling. I still am a kind of a fat kid. I still love eating cookies.
Who doesn't want to eat cookies?
Idiots. Idiots don't love eating cookies. I don't know. Maybe some people don't like cookies. Crazy people. Here's what you need to know about the law of cooling. A body cool, and I don't mean like a dead body, because that's really gross. I mean a body like an item.
Object.
Object? Sure, body. A body cool, well, you know, in physics they use body at rest tends to stay at rest, body in motion tends to stay in motion. A body cools proportionally to the difference between the body and the ambient temperature. A body cools proportionally to the difference well, that's interesting, between the body and the ambient temperature. Just that I know that you guys are smart, but you guys know what ambient means? Not an Ambien, okay? We're not talking about drugs, but an ambient. Do you know what ambient means?
Yes.
Okay, if you don't know what that means, it means the surrounding atmosphere of the body in this case. So right now, the ambient temperature would be the temperature of this room that you're in. I'd say 71 degrees. I would estimate, but that's the ambient temperature. I'm very comfortable. Are you guys comfortable?
Yeah.
Ambient temperature's nice then. Well, we're going to do this with an example. So here's my example. I'm such a dork that on Thanksgiving I literally did this. I literally did the math on this thing to find out how this would actually work, because I'm so dorky. Although I kind of overcooked my turkey, so it was really dry. Because I cooked it to 225 degrees internal temperature, and you don't have to do that. It's like 165 or something like that.
That's what gravy's for.
That's what gravy is for, that's right. I don't like turkey. I eat the ham, so let those other fools eat the turkey. They had some burned old turkey. So, a turkey is taken out of an oven at 225 degrees. Maybe the outside would be hotter than that even. It's taken out of an oven at 225 degrees. After 20 minutes, I checked it. After 20 minutes, it was 185 degrees. That was a well done turkey. Now, you need to know that at my house, it stays a nice 70 degrees all the time. Is that important to know?
Yeah.
Yes, because if I was really cheap during Thanksgiving and said, I'm not running the heater at all, it'd be like 50 degrees, in which case the turkey would cool off faster. Much more convenient for eating, but you have to eat in a jacket, so that's not super fun. If I kept it at 90 degrees, my electricity bill would be through the roof, but the turkey would not cool off for a long time. So they'd be very comfortable in shorts, but not be able to eat for a few hours. So anyway, my temperature in the house, or the ambient temperature, temperature of the house was 70 degrees at the time. Here's what I want to do. I want to find the temperature at any time. Then I'm going to ask you a series of questions. How much is the temperature after 30 minutes? When can I cut the turkey and not burn my fingers? So we'll ask a couple of those things. So firstly, we need to understand that y of t, let's define our variables right here. Y of t is going to be what? What does the y stand for in our
Time,
case here?
20 minutes.
The y.
Oh, the Y.
The y is going to be my temperature. That's right. So y of t says this. Give me the temperature. I know we're not using a t for temperature, but y stands for temperature here. Give me the temperature after a given amount of time. So this would be the temperature. Let's also define what t is. Over here, t was in years. Is my time in years here?
No.
It's going to take me 30 years to eat my turkey. No, that's silly. Okay, it's in minutes. So time in minutes. Time in minutes. Now, there's a few things that we need to identify before we start our problem. The first one is this. The first one, we got to figure out what our initial values are for this situation. So, can you tell me now that we have this, can you tell me how much y of 0 is? In fact, can you tell me what y of 0 actually means in reference to this problem? It's kind of good to know, right? I don't want you just to do these things by rote memorization of how to do differential equations and these cooling problems, but understand what it means. What does y of 0 actually mean?
When you first took it out of the oven?
Good, so it's going to be the temperature when I first took it out. Not when I start cooking it, but right when I open the oven door. Because it's going to start cooling at that moment when I take it right out of the oven. So at y of 0 means the temperature right when I remove it. How much is that?
225.
Perfect. Do we know anything else about this problem right now?
After 20
After
minutes.
20 minutes.
After how many?
20.
How am I going to write that?
Y 20.
Good. So it says, hey, the temperature after 20 minutes was 185. That's the two pieces of information I know. We always need those two pieces of information, where we're starting and how that temperature is declining or how the population is growing. We need another piece of information to be able to solve for our e to the k or our k or whatever we're talking about in each case. So far, so good? Now, the last thing we need to know is what the differential equation looks like. Well, it's important that we actually set this up correctly. You see, we're not going to have exactly the same model every time. We've got to think about what's going on. If we know that a body cools proportionally, that's cool. That's going to be, no pun intended, but that's going to be k times something, for sure. Now, if it says the body cools proportionally to the difference between, well, that's going to be something else. It's going to be a little different here. So, here's what we know. That right there would be, please pay attention, I'm going to change this. You don't need to write this down right now, just sit here and watch. This would be a rate of change that is proportional to something. This would be proportionality. We've talked about this before. Does that make sense? If I want the rate of change being proportional to just what the temperature is, I'm good. That's what this says. Rate of change is proportional to the temperature. Got it. Temperature right here is my amount. Do you understand that? It's not like the size of the turkey. Okay, that's not what I'm talking about. It's the temperature itself. The hotter it is, the faster it's going to cool in a given situation. As it gets closer and closer to the temperature of the room, it's going to cool more slowly. Does that make sense to you? It's proportional decay, but it's on that exponential model. So anyway, this would be proportional growth or decay. Now, I'm not directly proportional to the temperature. What I am directly proportional to, it says, okay, you're going to be proportional. It's going to be k times something. I'm directly proportional to what? The difference between what?
The body and the ambient temp.
Between the body. Difference means what?
Subtract.
And the ambient temperature. What's the ambient temperature? That's where that comes into play. So, I want you to understand why this is the way that it is. Firstly, do you understand that when I'm proportional, it's going to be k times something. That's what a proportional concept means. So, our rate of change is proportional. That means our rate of change will be k times some amount. It should tell you what it's in reference to up here. So, if it was just, hey, the rate of decline of my temperature is proportional to the temperature, it would have been ky. Not sure if you understand that concept. It's not though. It says the rate of change of my temperature is proportional, K times, to the difference between the body, the temperature of the body. Remember that Y stands for the temperature of the body and the ambient temperature. So this says it's proportional, the difference, the rate of change of my temperature is proportional, K times, to the difference between the temperature of the body and the ambient temperature. Show if you feel okay with these concepts. It's important to set up, right? Otherwise, we're going to be kind of stuck on this thing. Now for the calculus. We're going to go through it. It doesn't fit the model, so yeah, we're going to have to do a little bit more calculus here. Let's think about this in terms of a differential equation. We already got our initial values. That's cool. Can you do that differential equation? First, is it a differential equation? Oh yeah, it's an equation. It's got a first order differential equation situation going on here. Can you separate the variables?
Yes.
How would you do that? Divide by, no, I don't want to do that. I want to get y's on the left-hand side. I want the k's on the right-hand side.
It should be K.
Not going to do that either.
Divide, I thought it was the Y minus.
Yeah, let's just do that. Let's move this whole piece over here. So if I move this whole piece over here, I've got 1 over y minus 70 dy dx equals k. Hey, are all my y variables on one side and everything else on the other side?
Yes.
That's what I'm looking for. That's a separation of variables. Thanks for the emphasis. Yeah. Drop it like it's hot.
Throwback.
Anyway, what would I do at this point now that I have my variables on different sides? What do I do? Come on, you should know this. What do we do?
Integrate.
Some of you know it. Yeah, you're just not excited about it. Goodness.
Better be for an
Better,
integration
yeah.
be.
So we're going to integrate both sides with respect to, well, not really. In fact, I have this completely wrong from the very beginning. You should tell me the one mistake I've made, actually. I've made lots of mistakes, but today I made one mistake and no one caught it, actually. So I just kind of left it. I wrote it, and I'm like, I wonder if they'll catch that. I made a mistake from almost the beginning. What is it? DT. It's not with, there's no X. We don't have one. So be careful with I messed up right here and I just left it. I want to see if you caught it. We need to really be careful.
We failed.
You failed. It should be a DT. Listen, it's not a rate of change with respect to X. You don't even know what X is. Right here we have a rate of change with respect to temperature. It's the way the temperature is changing. Okay. With respect to time.
The mass
So,
dx.
temperature with time, temperature with time. The way the temperature is changing with respect to time. Right there. Temperature with time. Time.
Okay.
There we go. Now let's continue.
DT cancel.
Yeah, that's right, they do. So DTs are gone. Got that? We got an integral of 1 over y minus 70 dy equals integral of k dt. Can you tell me something about this side? Do we do k squared over 2 in this case?
No.
No, we're integrating with respect to, which is why it was so important we had this correct. You got to get the variables correct on this. It says k is treated like a constant here. K is a constant, it's constant variation. So we're going to have
Cake.
Pretty.
Keep going.
Oh.
Let's see one.
Ah. Okay. How about the left-hand side? We have 1 over y minus 70. What are you going to do with that? Are you starting to see how we're going to have lots of ln's right now? Lots of ln's here. So ln, we do a little substitution. We say, hey, derivative of this is only 1 though, so our integral is going to be pretty easy. We're going to get absolute value of y minus 70 inside of that for the argument of our ln. Show of hands feel okay with that one. Okay, calculus was pretty easy. Calculus is done. Now our job is to do what with this?
Find an arbitrary
Well, we're going to have to solve for y to do that.
constant. Yeah.
So let's get rid of the ln. How do we get rid of the ln? We got to move quickly. So treat that as an exponent upon e on both sides. ln absolute value y minus 70 equals e to the whole thing kt plus c sub 1. Here, ln's gone, we get absolute value y minus 70. Right-hand side, we get e to the kt. I've done this before, so I'm going quickly, times e to the c1. So far, so good? We're going to call c2 e to the c1. Since this piece is a constant, I'm going to call it a different constant. Therefore, I get absolute value of y minus 70 equals c2 e to the kt. Last thing we're going to do, again, we're moving quickly because this is exactly what we've done before. Do you guys see how similar this is from what we've done before? We're going to say y minus 70 equals plus or minus c sub 2 e to the kt. And then we're going to find our arbitrary constant c to equal plus or minus c to the c sub 2. Since this is going to be a constant, I got y minus 70 equals c e to the kt. Oops, sorry, I should have done that. Just need more space.
What's our general?
It's just the general. That's right. This is the general solution to this differential equation that we started right here. That's the general solution. Show of hands if you feel okay with the general solution. Now, how do we go from a general solution to a particular solution? What do we do?
An initial form?
Now, we've already used, well, did we use any of them? What have we used so far? Well, nothing really.
70 degrees.
We just use a 70, the Abian. Can we solve for our C? That would be our first case. Which one do we use to solve for our C?
Initial?
Probably this one would be easy to do, right? We'd plug in. Where would the 0 go? I want to make sure you guys are okay. I'm getting some kind of vague looks on your faces. Either you're tired or you're bored, or you don't get it. I want just the first two. Actually, I don't want any of them. So knock those off, everybody. Are you okay with getting this far on your own?
Yeah.
Pretty basic, separation of variables, do your integral, solve it all the way down, get rid of this stuff we've gone through several times now. Now, start working on what the K is and what the C is. Get rid of the C first. Find out what that arbitrary constant is with your initial value. That's why they call it an initial value, where you start at 0. So times 0 equals 225. Tell me how to write that. If y of 0 equals 225, then y minus 70 changes to what?
225 minus 70.
Yep. C e to the k times what, ladies and gentlemen?
0.
Perfect. Is this going to allow us to solve for C really easily?
Yeah.
Yes.
For sure. How much is e to the k times 0?
1.
So this whole thing is 1. This right, how much is 225 minus 7?
155.
Therefore, C equals 155. Done, we got it. Now let's rewrite our equation. So what we know now is that y minus 70, so we have our general solution, not a problem. Use your initial value to find a particular solution. So we're changing from general to particular by solving for our C. That's it. So general's here. Plug in the initial value. We got it. 0 for our T. No problem. That's why it works so nicely. This whole thing goes away. You get C itself. 225 for our Y, because the initial value at 0 is 225. This is a constant. This reduces to our C. Not a problem. Now rewrite it. We know that Y minus 70 equals, well, not C anymore, 155 e to the k times t. So essentially what we've done, we've used our initial value to change a general solution into a particular solution based on this initial value. That's what's making it particular. Because, listen, with differential equations, we're now forcing, this is weird, but we're forcing this family of temperature curves to go through this particular point. You see, this is the temperature curve for my house. This is it. For anything I take out of the oven in my house, it's going to cool like that because my house is 70 degrees. Does that make sense? Now I'm saying I took out something at 225. Figure out what happens. Now that changes it to, oh, how much was your temperature? 225. That's now a particular temperature curve. Had I taken it out at 450 degrees, it'd be different.
A different C.
Whatever that was up there, okay? It'd be 450 minus 70, and that would now be your C. Show of hands feel okay with that one. All right, so cool. What now?
Solve for whatever you want.
Solve for whatever you want to solve. What do you mean solve for whatever you want to solve for?
Well, you need to answer the question.
Time in minutes.
I just asked, what do we do now?
Oh, you want us to find a general time?
No, we're missing something up here right now. We got to get rid of that e to the k. So how do we get rid of the e? This isn't going to let us do anything right now. If I say, hey, find the temperature after 30 minutes, you're going to go, cool. What would be 30?
T.
What would k be?
We don't know.
I don't know. That's why you have to be given the second piece of information. So there's initial value. Initial value solves for your c, your general. This is going to allow you to solve for your k. Does that make sense? So now we plug that in. So from here we go, okay, this is cool. This is a particular solution right now. But this next piece is going to make it so that we can solve for my variation. So if y of 20 equals 185, let's continue to plug this in. Go for it. What do we do?
185 minus 70.
185 minus 70 equals 155.
E to the k times 20.
Perfect. 20 is our time. 85 is our temperature. Now we solve it. Let's solve for e to the k like we did before. That way we don't have to worry about those ln's. 85 minus 70
115.
equals 155 e to the k. I'm going to write it like this right now, just to the 20th power. E to the k times 20 is the same thing as e to the k to the 20th. Then what do we do?
Divide by 155.
Let's do that. Let's divide and let's simplify. What do you get when you divide 115 by 155 and simplify? How much you get? 23 over 31?
Oops.
Now let's get rid of that exponent. How do we get rid of that exponent? No, I don't want to do ln right now. I don't want to do that. I want to leave the e to the k, because what I'm going to do is substitute for this whole entire piece right there. How do we get rid of the 20, the power of 20?
Multiply by
Okay, so by multiplying exponents, we're taking each, listen, the math on this. By multiplying our exponents together, we're taking each side to that power. So in our case, we're going to take this to the 1 over 20th power, and this side to the 1 over 20th power. So 23 over 31 to the 1 over 20th power equals e to the k. Because these things are gone. What that does for us, it changed now our particular solution into something that will work only with this situation with our turkey. Okie dokie? Actually, so the 225 kind of did that too, but that would be for anything taken out of the oven. But if I took cookies out of the oven at 225, well, they're probably not going to match this situation. So this is just for this particular turkey. Does that make sense? Mm-hmm. So general worked for anything in my house. Particular said anything in my house taken out of the oven at 225 degrees. This one says anything taken out of, sorry, the one we're about to make, says anything taken out of the oven at 225 degrees in my house at, look at, in my house at 225 degrees. And now this last one says, and fits this scenario where after 20 minutes, it's 185 degrees. I need to make sure you guys get this. Are you okay translating from this guy to this guy using this?
Mm-hmm.
This was, hey, same thing. E to the k is now this piece to the 1 over 20, but since I'm multiplying by t, I get t over 20 instead of 1 over 20. Show of hands if you're all right with that one. So let's go through it one time real quick here. That minus 70 came because the difference between the temperature of the body and the temperature of my house. So this is for my house at 70 degrees. This came from solving for a particular solution, particular solution, given that the item starting out, the body starting out is 225 degrees. Does that make sense to you?
Mm-hmm.
This comes from this particular piece of information saying that this has to fit the scenario that after 20 minutes, it's 185 degrees. If the body doesn't fit that scenario, this won't work, but I could maybe change that. Does that make sense to you? Okay, so now we continue. Let's solve this for y. Just one little step. How can I solve it for y? Yeah, just add 70. So y equals 70 plus 155, 23 over 31 to the t over 20. I get two questions. First question. What will the temperature of my turkey be after 30 minutes? Where would the 30 go?
T.
Pretty easy now, it's just plugging numbers in. So we'd say the temperature would equal 70 plus 155, 23 over 31 to the, well, T stands for, this is why we defined it, okay? T was time in minutes. We had it on the board earlier. T was time in minutes. If I want 30 minutes, I'd put 30 over 20. Y stands for our temperature. That's what we said. Y in terms of T was our temperature. We already defined that. How much is that? Did you figure it out?
169.
Yeah, about 169 degrees. That's still a really hot turkey. Let's see if it fits. Listen, after 20 minutes, it was 185. It's cooling, right?
Mhm.
After 30 minutes, it should be cooler, was it?
Yeah.
Hey, that works. Now, let's find out this. How long does Mr. Leonard have to wait to cut his turkey so he won't burn his fingers?
What's the?
How long does Mr. Leonard have to wait to cut the turkey? Darn turkey, burning my fingers.
Did you really?
So I always burn my fingers on stupid turkey. I cook them too hot. How long does Mr. Leonard wait?
Are you impatient?
Yep. I'm hungry. Cut turkey, so I don't burn fingers.
So he doesn't.
So I don't burn. Okay, go.
What is
That's what I'm thinking.
Oh,
like,
dang it. Okay, so burn my fingers. So I'm a hot guy, so let's see, when will I burn my, I can touch things that are about,
Average cup of coffee is 140.
yeah, right, but coffee would burn my fingers if I put it in there. It burns my mouth all the time. So I'd say, let's say 125 degrees. I think I can do that. I think I can handle 125 degrees for a little
we
while.
need to test that.
It's hot. 125 degrees is hot.
I could touch a tortilla on the comal and it doesn't burn me. Like,
I don't know what you just said. But I imagine it has to do with food.
I got the cooking.
The water actually at my old house was like 130 degrees, and that would burn me. So I'm guessing 125. I have to go. Okay, but we'll still stick with it. So the temperature that's not going to apparently burn my fingers is 125 degrees. Question: where would the 125 degrees go? Yes. So for our model here for this particular turkey, we'd have 125 degrees equals 70 plus 55.
155.
That's what I said. 20. 23, 31, T over 20. And then we start solving this thing. To omit time, I'm just going to give you the answer because we're going to go over here. We're already over here. So we'd subtract 70. We'd divide by 55. We'd take a natural log on both sides. We would move our T over 20 to the front. We'd multiply by 20, divide by ln of 23 over 31. And what you end up getting is a time of, what did I do? About 69.4 time. It's minutes, because we define our time to be in minutes. So in just over an hour, I'm going to be able to cut this turkey and serve my guests some really dry meat.